Good morning, everybody here, and good morning, our colleagues and students who are in YouTube channel of uh, Brazilian Chemical Society Division of Natural Products. It's a great pleasure to have you all. And today you have a second class of the plant-based metabolomic course, and now I invite Professor Short to start the second class. Thank you.
Thank you very much once more. Day, second day. Actually, yesterday I was too much talkative. We have to finish this part, but always the first day is kind of a tuning period. Tuning time. I want to know you, you want to know me. So I hope you know me, right? How can I react to you? Or what kind of question do I have for you, right? And also today, I found three more people joining, right? New people. One, two, right? I remember. Put together. It's good. Although I cannot remember the face, but I have a name, but I don't remember the face. Usually when I started the course, the first day is 100, for example, 100 people. But at the end, I come up with only 20%. Yeah, so always the learning, the first one is a life journey. You have to learn every day. But for most people, the one is not speed. Yeah? To learn fast, it doesn't matter. But to keep your learning attitude, this is very important. Okay. You agree? Yeah. Okay, then is yesterday, what you learned yesterday? Primary metabolites, yeah. Then what's the difference between primary and secondary metabolite? Secondary metabolite yesterday, nowadays, one group, some people, they said instead of secondary metabolite, we call specialized metabolite. What's the difference between primary and secondary metabolites?
Primary metabolites are essential for the metabolism for the survival of and for the microorganism. And specialized metabolites are the luxurious chemical compounds they produce in certain situations.
Luxurious is between you and me, but that's a scientific word. It's a special topic. Okay, it's very nice. Fatima, where is the champagne? We have to have champagne. She knows very well. Okay, that is Miss. So, what's the representative group of primary metabolites? There are three groups yesterday. Yesterday I mentioned. Protein and sugar. Very nice. One left. Lipids, fatty acid, right? Okay. Then, Mister, so you can point out who is you. What's the difference between lipid and fatty acid? No. Uh, what's the difference between fatty acid and lipid?
Uh, yes, the part of the liquid molecule.
What molecule? Okay. The lipid is part of our molecule. What is the other part?
Nice.
Fatty acid, there is a saturated, unsaturated fatty acid. What's the difference? What's the unsaturated and saturated? What's the difference between them? Huh? Double bond, double bond. What double bond? Mister. I mentioned yesterday, usually in plants, not plants, most of organisms, fatty acid yeah, has even number of carbon atoms. Why? I don't remember. Yesterday, do you remember? I mentioned fatty acid always mostly even number, but sometimes it's mitochondria they produce odd number, 1, 3, 5 or something. But why do they produce even number of fatty acid? Right? Because always building block is C. Everything is reminded, right? Okay, let's start. Today, the secondary metabolism for our luxury slide. Let's study first the monoterpene. Monoterpene is terpenoid. Terpenoid means terpenoid in terms of biosynthetic pathway is consists of a C5 unit. C5 unit. Yeah. But then if it's a C5 unit, why they put the C10 monoterpene? It should be diterpene because C5 two times means is a C10, then it should be diterpene. Why they put monoterpene with C10? Any suggestion or anything comment? Because in the nature there is no C5 metabolites. 5 metabolites. Only C5 always is to conjugate to first is a C10, monoterpene. Monoterpene is a C10. Then, is it true? I said there is no C5 compounds. Is it true? Actually, C5 compounds there is. We call it hemiterpenoids. Hemi means half, right? Hemisphere, right? Hemiterpenoids. I don't know about the recent studies, but when I learned it, hemiterpenoids, C5 compound, is not from terpenoid. It's not from terpenoid. Always the smallest carbon number terpenoids is monoterpene, right? Have you heard about the essential oil? Yeah. What's the essential oil? It's oil. Something like oil. It's a very essential. No, it's not true because of course every day I wear perfume, but I can live without perfume, no problem. Essential oil is the volatile compounds from plants, usually from plants, but it consists of monoterpene, sesquiterpene, and plus volatile or non-polar phenylpropane. So, in terms of the chemistry, essential oil consists of monoterpene, sesquiterpene, and phenylpropane noise, but not all phenylpropane, volatile phenylpropane. So, when you smell something from plants, these essential oils, volatile compounds consist of one of them or either 2 or 3. So monoterpene or any monoterpene and diterpene, so sesquiterpene and phenylpropane. But diterpene, some people they include some part of diterpene and maybe it's part of essential oil, but it's a debating question. Then it's monoterpene. Let's talk about monoterpene. It's a C10 unit. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C5 unit. Oh, everything is a C5 unit. Narrow phosphate, and maintain. Maintain, where is from? Because yesterday I told you, one of the bottleneck was hurdle to learn natural product naming, right? Because naming is, they don't follow the IPA naming. Always they use their own name. Naming from the source of plant. Maintaining. Where is from? Can you guess? Menthol. You are genius, right? Menthol. Already I can smell it. And limonen? No. Where is it from? Lemon, citrus, orange. It's orange. Inen, where is it from? Venus. You are genius. Okay. And garden and Houston. This one is from those kind of monoterpene. This monoterpene now is many, I think it's not now. Some decade, some years ago, it was revisited. For what? Monoterpene is very important for perfume, for odor, for smell. one of the many groups doing plant microbiome or environment interaction is volatiles or monoterpenes are revisited, which means they are studying again. Studying again. Why? Why? Nowadays, many people, you are communicating with your friends by SMS and email or telephone, right? You don't have to meet all the people. Plants also, they kind of metabolites. Plants also, they are very sessile organism. They cannot move. When they are communicating, they send this kind of volatile gases. Of course, in terms of application, it's very important for perfumery or other odoring or flavor or fragrance. But also in terms of the plant physiology, this monoterpene, okay, in broad sense, is essential oil or volatile. It's a very important plant and other microorganism interaction. So monoterpene, you can see here monoterpene. Then monoterpene, usually they are located. Do you know monoterpene? What's the role of monoterpene? Because it's they are communicating with each other. They are communicating with each other, which means they are always ready for emergency. So which means all the volatile located in epidermis. Epidermis, lavender or whatever, is not in the cell itself, not inside the cell. It's usually epidermis spaces. Epidermis spaces, which means it is epidermis, they are ready to be released. Then usually this monoterpene does not exist glycoside. Usually secondary metabolite they exist as a glycoside. One of the hypothetic role why they produce glycoside to store. But of course it's not always correct, but it's a store. But monoterpene, they don't have to be glycosides. But they don't have, so usually monoterpene is existent changing cases. It's not glyphosate, but only one exception. One of the monoterpene is iridoid. This iridoid looks like this one. Iridoid is iridoid. Iridoid always sugar one. Glyphosate. This sugar one, and this one is this one is glucose. It's alpha glucose or beta glucose. Beta glucose. Why? Because number one position is low. Yeah, it's a blocked. It's a block. So we say it's only beta glucose. But it's open, then they have two. I told you, yeah, there are several positions. Here. Five positions is available in one sugar, one glucose attaching point. If this one is attached here, this one is open, number one position, then this compound has two forms, alpha form, beta form. But fortunately, in nature, glyphosate always, not always, most cases, number one position. Number one position, that's why it's a beta glucoside form. In iridoid cases, very exceptionally, the glyphosate form is exist, but this glyphosate form is glucose, but 99%, 99% is sugar is glucose. We don't know why because it can be rhamnose, yeah, because of flavonoid or saponin or other blood types, always glucose, rhamnose, xylose, arabinose, galactose, whatever they can attach. But iridoid cases, whatever reason, I don't know actually. Somebody already investigated. For me, I don't know. Glucose is 100%. So if you find it iridoid, it's kind of monoterpene, and you find the glucose, you found the glyphosate, then it's 100% it's glucose. But interestingly, the saccharoguanine is one of the famous precursor who produce indole alkaloid. Indole alkaloid means terpenoidal indole alkaloid, vincristine and vincristine. One of the part is indoles, like from tryptophan, and the other part is from this roganin type of iridoid. In this case, here, number three position, double bonds, single bonds, double bonds. Here, then it means conjugated. They are always exchanged. So that's why this one must be double. But when you measure the NMR spectrum, you found three signals. So that's why many people they misunderstand. When you measure NMR spectrum, we found only one form, but actually it's not true. Yesterday you learned it, glucose, you measure glucose, alpha glucose, beta glucose, and D form, L form, and furanose, pyranose. All the mixture is fine. And second one in case, this one is three forms is generated. So that's why then if you don't know this information, when you measure, oh, this one is a mixture. No, it's not mixture. It's because of they are exist three forms. It's like in religion. In religion, you are probably religious trinity. God exists three forms, right? This is what this kind of yeah. Of course, it's a kind of platformers, but I hope you understand for this case, Trinity cases. But then to avoid this one, to avoid this one, it's easy. It's a tip. The tip. When you add a strong acid like HCl or some strong acid, it becomes one acid. So that's why many people think, okay, if I added acids, probably my compounds can be degraded, but it's not always. In these cases, when you add acid, then it becomes one single. And the other one is a sesquiterpene. So now C10 is a monoterpene. Then how many carbons exist in diterpene? C20, right? But now C15 after C5 unit and another unit, monoterpene, and the other C5 unit, then, okay, then scientists made a mistake because they studied the C10, they don't know how to put the name C15. So that's why they put sesquit in between, yeah? Diterpene, C20, and then C10 monoterpene, and mono and di in between is sesquiterpene. Sesquiterpene, right, is one of the most diverse chemistry because someone said now there are many groups. There are many groups in nature: flavonoid, saponin, terpenoid, alkaloid. Then if I ask which group of metabolites shows more highest chemical diversity, they said sesquiterpenoids. This sesquiterpenoids, as I mentioned, is a part of essential oil. Essential oil here, C15 here, most diverse group of compounds, more than 100 skeleton. Of course, it's not only changing methoxy or methyl group, but skeleton itself is a very diverse compound. And cytotoxic, sesquiterpene and lactone. So in this, you can count it, it's a C5 here. This group in organic chemistry or ketone is a lactone. Yeah. Is lactone, so sesquiterpene lactone. So under the sesquiterpene, there are specific group, sesquiterpene lactone. It was one of the famous targets for drug development in 1917. This sesquiterpene lactone shows the highest cytotoxicity against the cancer cell. So they wanted to develop a new anti-cancer drug based on this sesquiterpene, but more or less. Now some group in German, they are using this one as a structures, but still it's problem. What's the problem? When you develop a new drug for the cytotoxicity, anti-cancer reagent or anti-tumor reagent, what's the most important problem?
Selectivity.
Huh?
Selectivity.
Selectivity. Very good. Selectivity means it's if I translate it to another simple words, it should kill only cancer cell line. But if the compounds kill you, then it's not worth to use it. This one is a selectivity. There is no selectivity. It's very toxic, but you will die. This is a problem. So, but now it's revisiting. Some German group, they are starting to modify their semi-synthesis, sesquiterpenoids, and diterpenoids. Diterpenoids means how many carbon? C20. That's simple. C20, you can count it. Now, from diterpenoids, you can see very familiar structure. It's a ring. Is formulated. Of course, this one is ring generated, but diterpene is at least more or less 3 rings are generated. It's a very complex structure. So there are many also chiral center. Diterpene is an interesting compounds. What's the location? What's the location for them to be present in plants? Always, most cases in park. Outside of tree, So that's why when someone in museum, when they want, because if you found a nice painting, painted by Van Gogh, Van Gogh or Rembrandt. Yeah, Rembrandt. Of course, it's, the painting itself is very important, but they are interested. Where are they from? It's canvas, wood. Then when they analyze metabolic profile targeted on nitrogen, they found okay, these trees came from maybe from Sumatra or Java or China. So this nitrogen is very important for the chemotaxonomy or fingerprinting of wood tree, but it's not all. The other one is you heard it, steviosa, your best friend in South America, Paraguay. Paraguayan, I don't know his best friend, but then in Paraguayan contributed a lot. Not current Paraguayan, all the times. Paraguayan produced, found in Paraguayan, India, steviosa, sweetener, and second one is mate. The next Paraguayan says mate. They found those two one. This steviosa is howland type of the compound. This steviosa is compared to sugar is 200 times sweeter than sugars, and also is low calorie. It's low calorie. So that's why nowadays Brazil is allowed to use steviosa. Right? Some decades ago, only Korea, Japan, or these other countries, they are allowed because there was a debating question. When they tested it, for example, it's not real statistic, 100 people tested it, 99 people, they said there is no carcinogenic. But one people found it carcinogenic, which means in terms of the statistical significance, it can be ignored. But this one is related to our toxicity. So that's why they delayed, postpone. But now even in Europe and Brazil, well, states, yeah, they are using this stevicide as an alternative sugar. But in long times ago, in Korea, they produced their own liquor. Probably you heard the soju, one of the Korean popular liquor. This liquor made from steviosa. But when they exported to Australia, by mistake, it was the soju, the liquor, Korean liquor, traditional liquor, include this steviosa. Everything is, I don't know, someone drink 1 year, it's officially it's banned. But now it's okay, steviosa. And the other one is, which one? Aconitin. Have you heard about aconitin? One of the subgroup is diterpen. I'll explain later about alkaloid. Diterpen is after making skeleton diterpen, and nitrogen is we call it. It's not true alkaloid, but it's in broad sense it's alkaloid. Diterpenoid alkaloid. This diterpenoid alkaloid, we call it. This one is very active compounds. Aconitin cases from aconitin species. It has been used for the poison long time ago in Asia, in Korea, or in China. I don't know in Japan. They used if they were sentenced, for example, in high noble people is sentenced to death by king, and then there are several ways. Of course, you hang on or cut your head, beheaded, that way. But if it's very noble people, they want to give a kind of a mercy for them, then they give a poison. In that case, it's appointed. It's included. And also in Europe, they use, because many medicinal plants, they found this simultaneously, but usage sometimes application are completely different. It's aconitin. Have you heard about aconitin, another application in Europe? Long time ago, not now. In Iceland people, you know Iceland where it is? It's a kind of Viking Iceland people. I think it's Iceland or Norway. They use this one as a whale hunting. You know whale hunting? The big fish, it's not fish, big mammalian. Whale hunting, they use this one. They don't think. And taxon group, you heard of taxon from taxon, taxon, and or we call it taxol. But this taxol, many people they think because it contains nitrogen, it's alkaloid, but it's not true alkaloid, it's dialkaloid. So in dialkaloid group, there are many compounds. There are many diverse active compounds. And triterpenoid, how many compounds do you expect? C30, right? You can count it C30, oleana, ursa. Those two groups Udanan type. Yeah, Udanan is one. Bursa, Fidalan, and Prostan, Alastan, Cyberartan, Protomitan. Those are main subgroup of triton. It looks very complex, but actually, when you analyze quantum material, the main triton that we found in Udanan type, what Bursa, one of them. What some plants they contains two. It contains two. These triton band, depending on the subposition of the structures, yeah, it said it's oleana, fursan, tridana, prostan, danostan, then it's already tetracyclic. Sorry, 1, 2, 3, tetracyclic. And this one is enta, 1, 2, 3, 4, 5, 5, at least, yeah, tetra or tetracyclic defenses. Now, oleana, fursan, that is a very common triton colloid. And the other one is a protomitan. Protomitan is a protomitan C molecule here. This one taste. You know the taste of protomitan is? The same as pashnoid yesterday. What's the taste of pashnoid? Let's see. Alicia, what's the taste of pashnoid? Bitter. Bitter, right? But I don't know which one is. Protomitan is also very bitter. Very bitter. But bitter means in traditional medicine, usually they have been used for ulcers. Ulcers because they taste it, ulcer is used. Though this concomitant containing plant material has been used a lot for the ulcer in traditional medicine. It's not more medicine, it's traditional concomitant. And steroid cases. Steroid, actually I have a question. Now, C10 is a monotherapy. C15 sesquiterpene. C20 is title. Then you might have a question. Where is the C25? Right? C25. First question is, do they exist? C25? Yes. Yes? He said yes. Then what's the group name? You already used sesquiterpenoid. Sesqui already used. Then? Sester. So C25, yeah, also scientists, yeah, thought about it a lot. Sesquiterpenoid. In plants, it's a very rare case. You can find it, but it's a very few cases. C25 terpenoids, you can find it usually in marine organisms. Marine organism, you can find C25. So that's why I didn't mention here C25. And C30 is a triterpenoid. As a triterpenoid. And steroids. Actually, basic skeleton of steroids is very similar to triterpenoid, but three missing. So in terms of the biosynthetic pathway, squalene is a precursor. You learned it from Fatima's course. After squalene, they are going to the triterpenoid, lanostan. Lanostan is a precursor. This lanostan is one branch. After C3 deletion, it's a steroid. Then how can I distinguish whether this one is steroid or not? Because sometimes steroids after making 27 skeletons, sometimes 1 or 2 addition, then she's 25, or sometimes she's 30. What's the chemical difference? Usually, please look at here. Here, this is like a 2 metabolomics. Here, usually this one is the triterpenes, but steroids, they don't have steroid data. C27. Then, now it's mammalian terpenoids, mammalian steroids. One of the famous one is cholesterol. But if cholesterol, I said the mammalian steroid. But is it true only in mammalian? Some plants contains also cholesterol, very low plant. Low plant means it's a primitive plant. Like polypodiaceae, some plants they produce cholesterol. But when you analyze the plant extract, please imagine what if you find cholesterol in your plant extract. Now you are ready to report, okay, this plant contains cholesterol. But then reviewer or other people will have some question. How can we sure this one is from plant? Even you extracted the plant, who knows, you collected from wild, and now maybe some wild animal, other insect can be co-extracted in your plant material, like wild animals poo, urine, yeah, those kinds included, and you extract it, and you found it, you claim it is a plant extract, we are not sure this one is from plant. But after some investigation, some plants, low plant, very low plant, in terms of evolutionary, these cholesterol are included. But in the plants, what are the major steroids is beta-sitosterol, and stigmasterol, and the other one, campestre, C-A-M-P-E, campestre. So always in plants, when you measure, although they are secondary metabolites, when you measure any plant material, there are three major steroids, always ubiquitously, not specific, you can determine. Still beta-sitosterol, stigmasterol, campestre. Even the ratio are the same. Testosterone, when you isolate the testosterone, 66%, and then the campestre around 30%, stigmasterol around 30%, and then the other part, 7 or 10% is campestre. So, testosterone, stigmasterol, campestre, 6:3:1 ratio, any plant material. Then, although they are secondary metabolite, why they can always produce these three steroids in the same ratio? Because steroids is not only secondary metabolite, also it's a part of cell membrane. Because any plant material contains a cell membrane, these three steroids are exactly the same. So that's why when you want to buy beta-sitosterol, this one, beta-sitosterol, when you want to buy from Sigma Aldrich, the purity, 60%, more or less 60% is very cheap. More or less is, for example, I don't know exactly by heart, but it's around 20 euro, 100 gram, 20 euro. It's very cheap, 20 euro, $20, 100 gram. If you want to increase the purity 100% or 99% of sitosterol, then which means 1 milligram is around 100 euro. Why is it so expensive? It's because this one is sitosterol, campestre, and stigmasterol. They always is a very similar chemical structure. It's very difficult to isolate, purify compounds. Then aldosterone, where are they from? Where is it from? Fungus. What's a fungus? Because aldosterone is one of the characteristic steroid of fungus species. But be careful, when you analyze plant extract, as I mentioned before, sometimes you can find fungus. Why? Because your plants are infected by fungus. But usually aldosterone is from fungus. Now, C14, I don't know whether C35 exists or not. I don't think I find C35, but in C14, it must be tetrahydrocanol, right? But they never follow our expectation. It is a carotenoid. Carotenoid means carrot from carrot. What's the color of carrot? That color, yeah, or this color, orange color. So that's why carotenoid is usually very colorful, like yellow, very strong yellow in red. So how can you do? How can you expect a color? Double bonds, single bonds, double bonds, single bonds, double bonds. All of them. There are many conjugative structures in organic synthesis. All they observe in the visible wavelength. So that's why this carotenoid, one of the famous one is beta carotene. Where are they from? It's from carrot. What? Tomato. Red color, tomato. So now you have a question. Now you buy flowers in the flower shop. Yeah, flower shop, red color, rose red color. Then you might be question, you might have a question, what kind of compounds can make rose red? Is it carotenoid? Carotenoid is a very red color. No. Usually rose color, red one, rose, no rose, rose red is from anthocyanin. I will explain. It's a kind of flower. Then tulip, you know tulip. Tulip red color is a combination between anthocyanin plus carotenoid. But their chemical character is completely different. Carotenoid is very lipophilic. So they can located, they can present outside. But anthocyanin, as you see, is a very water-soluble compound. It's inside the case. Its location is different. And also, when you cut very big tree, like a thick tree, when you cut out, then inside is very red. Yeah. That red color, I will explain later, which compound by the way, is an anthraquinone. Anthraquinone also is a quinone type of the compound. Anthraquinone, when you isolate the compounds, they look like that red color. Anthraquinone, anthocyanin, and carotenoid, all red color, but depending on the location, anthraquinone never be in the epidermis, never be in the cell. It's always inside the big tree. So that's why depending on this one, the components of red color are completely different. So carotenoid, yeah, it's not tetrahydroid, it's a carotenoid. And analysis of carotenoid and stenoid, of course, mass base is the best. MS, particularly arsenic mass is best. It's more powerful than animal for individual carotenoids. GC mass for glycan, GC mass, as I mentioned, more or less limit of molecular weight is 600 or 700. But most of the terpenoids, except for essential oil, they exist as a glycoside. If there is a glycoside over 600, you cannot detect in gas chromatography. So that's why GCMS is a little bit limited. After hydrolyze, what if it's a glycol, maybe you can use it. And methyl and annually proton of sugar characteristic featured in animal spectrum. Always now, when you look at here, animal spectrum is here. Now, when you see, you cannot assign all the signal, which means which signal is which structure, which signal which group it is. It's impossible. Instead, always in the terpenoid analysis, animal spectrum, this methyl position is very important. It's a very characteristic number. Please keep in mind. Here, after that, terpenoid steroid glycoside is saponin. You heard this saponin? Yeah, saponin. Saponin means is a terpenoidal plus sugar. We call it terpenoidal glycoside. Any kind of, it's not terpenoid. Actually, if I say triterpenoid. Triterpenoidal, actually it's a triterpenoidal plus sugar is a saponin. But steroid also, no, it's steroid. It's this steroid. Stigma steroid also can exist as a glycoside form. But we, in steric sense, stigma steroid, campesteroid, or this kind of common steroid glycoside, we never say saponin. Steroid means very specific sphenoid with another ring. Another ring is other rings. Okay, so maybe it's the most common saponin is triterpenoidal saponin. Steroids, not all the steroids, very specific steroids. Like a diosgerin type of the compounds, diosgerin glycoside is a saponin base. Saponin character, it sounds like a saponin is soap, right? Soap is a bubbly. Yeah? So that's why when you extract saponin, you can see a lot of bubble. And why is bubble? What's the mechanism of the soap? Because there is a hydrophilic group and hydrophobic group. They interact with each other. When you look at here, saponin cases, this kind of triterpene is hydrophobic. They put lipid. And if there is another sugar in here, sugar, carbohydrate, it's very hydrophilic with the water. So that's why it becomes bubbly. So now, when you extracted the saponin rich plant material, and you want to evaporate, you will have a lot of problem because always bumping. Yeah? Always bumping. You have to be always together with the extract. You have to be careful. And also, one point, when you do animal measurement, for example, you isolate the saponin, and you want to dissolve in the animal solvent, but the problem is if it's water solvent, water included solvent, then there is a bubble. Of course, you want to remove the water, but there are very micelle kind of bubble inside the solvent, then it becomes animal spectra broad. So that's a be careful when you do saponin analysis, animal solvent, very you better to use non-water solvent. Of course, but saponin is very well soluble water or others. Then please try the methanol or some feeding type. It's a free for free. Now, what's this? It's a stereoside. Stereoside. When you measure mass spectrum, mass spectrum, stereoside. I told you stereoside is very sweet. Sweet. Is stereoside. Now, here, please look at this one. This one is a molecular weight. It's molecular weight. Mass spectrum, nowadays, most common method, soft ionization method. Right? Soft ionization method means why they put the soft ionization method? Now, which kind of ionization type do you use? ESI, we call it ESI, electrospray ionization. But when you heard it, maybe I know some minutes, mass spectrum, yeah, the most traditional old type of mass detector after mass, then ionized material must be actually the material must be yeah, ionized, ionized. Because normal compounds like this one, they don't have, I don't have an ion, right? Because I'm normal, neutral, then it cannot be detected. So that's why there is artificial, not artificial, additional device to give energy to make them ion. That's the ionization first requirement. First requirement. This ionization, easiest way is how to make him ionized. I took out one electron from him, then he is ionized, right? Plus charging. But then you might have, if I take one electron from him, probably it's different because he lost one electron. The size itself, electron is like a football. Yeah? And molecule is like a Maracanang stadium. So 1 volt miss is no problem. So that's why to make this electron old-fashioned, but still is being used in gas chromatography, EI spectrum. EI, electron impact. How can you make an electron impact? Now is a simple. I want to make an electron. Then I want to give a electron spark, electron voltage, 70 electron volt. But he was shocked, one lost. That's why I can detect it. That's the electron impact. Pros and cons. Pros, electron impact. It's very nice. Any kind of compounds, I can make them ionized. Cons, problem, fragmentation, because when I give a 70, usually 70 electron volt, they decide it's very reproducible. When I give a 70 electron volt, now it's become angry. So then, right, all the bonds break down. This breakdown means I cannot detect molecular ion instead of fragmented ion detect. So that's why when you are using gas chromatography, only fragmented ion detected, you cannot detect a molecular ion. That's why till 1980, all the scientists dreamed, I really want to detect a molecular ion because that's my dream for the structural elucidation. But EI effect is problem, gas chromatography. Another issue is if the compound, particularly if the structure contains OH functional group, and because many organic compounds, at least one OH, if OH is included, then you cannot detect because OH easily deleted as a water H2O. So there is a dream. So that's why 2002 is the mass year, mass spectrometry year of Nobel Prize in physics, in chemistry. Two Nobel Prize laureate is one of them is because of development Mardi. Second one is in chemistry, he developed a ESI, electron spray ionization. This ESI means, okay, I don't want to give a electron spark, but instead, also another dream before ESI development, they want to connect the mass spectrometry with the chromatography. But only gas chromatography, because it's a gas, it's an inert, gas chromatography, EI spectrum is connected. But when they want EI to HPLC, because HPLC was the most common isolate separation method, but EI plus HPLC, then in between there is an interface. Solvent should be evaporated within 1 second. It was technically impossible. Then the scientist, he developed it. Then why not? We can use a solvent without any evaporation. Then they make a very narrow nozzle. Here HPLC, and here is detector. Instead, I put the very narrow nozzle. After HPLC, they pass here. Then it becomes foggy. You know fog? Mist. Fog each micelle or foggy short time. We still don't know the exact mechanism, but when they do ESI spectrum, we don't need any special device to give electron charge. Only this very narrow nozzle. So that's why nowadays system, any kind of now HPLC LC we don't have to put ESI because they use the ESI method, electron spray ionization. Soft ionization. Why soft? Because I don't want to give a 70 electron volt. Only resistant they give. Very nice, right? In the nature, there's nothing perfect. What's the problem? What's the problem of ESI? First one is pros. Pros is you can detect at least molecular ion because now is they don't care about OH, it's detecting molecular ion. But the problem is we had forgotten in EI spectrum, although we couldn't detect, we are not interested in fragmented ion, we couldn't detect molecular ion. This fragmented ion is very robust, it's very useful for the fingerprinting. Even though I don't have molecular ion information, but this fragmented ion, particularly nowadays still being used in NIST database, the American, NIST database, then this fragmented ion, but when you do ESI system, we don't know any fragmented ion. We solely focus on molecular ion cases. That's a dilemma. So that's why now revisiting EI spectrum, ion tremendous. Now is ESI combination is okay. But anyway, when you look at this one, I told you ESI spectrum contains only shows molecular ions. But here, these cases, now this kind of ester bond is a very weak bond. When you do even ESI, you cannot detect of this one. Only M minus glucose is this one is O, it's okay. But COO, right, is easily detected. Now, when you look at it without any information about this structure, probably you will recognize this one is ESI, the molecular ion structure. That's the 11. Okay, 641 and 803. So even though we believe ESI spectrum shows the molecular ion, please don't forget there's always chance you cannot detect molecular ion case. Then how can you be sure? How can you be sure whether this one is a molecular ion, whether this one is molecular ion, or else you can use it. If you have some information, you have to use it M plus NA, M plus K. Usually fragmented ion does not produce properly the adapted ion. Okay, so anyway, this one. And what's this? Glycine. Yeah, glycine is from glycine. This glycine also contains a lot of here sugars. Then here N minus glucose here and here another M minus. So you even this glycine is you cannot detect molecular ion. So please keep in mind our mass spectrum based on ESI spectrum is ESI network. Still you can detect, you cannot detect sometimes molecular ion. Always keep in mind. And I forgot multi-matrix acid desorption, ionization, laser desorption, ionization, multi. Have you heard about the multi spectrum? Multi. What's the mechanism of multi? Because there are two ways now is a biological science, biology, biochemistry. Two methods is often used, ESI system, including ABCI, and multi system. Multi system is different method. Always, multi is matrix system. I put this compound because if I give energy, like a 70 electron bond to him, it's too strong. So that's why I put compounds in the matrix, like a glycerol. Glycerol very sticky compound, and I give energy via laser to this matrix indirectly this attack. This is a matrix. When they found it, when they used this one, it was a very soft ionization, like a big molecule, like a protein, polysaccharide, those big molecules you can detect it. So that's why when you assume, when you want to know molecular ion of big molecule, polysaccharide, protein, whatever, you need both information, ESI spectrum and multi-spectrum. But for the small molecule, ESI is better. But many cases, of course, sometimes you can use it for the small molecule, but this one is small molecule. Many cases a little bit limited to higher molecule. But sometimes they are useful. Here, the ursolic acid in animal spectrum. Let's look at this one. Now, I told you when you do structural distillation, this one is tricarbonate, always is methyl group. So from 0.7, 1.6 ppm is very important fingerprinting. Now you think, you assume is your compound looks like a tricarbonate. But now you want to elucidate the compounds. Then first step is you have to find all other previous reports. Then which signal should I compare? Then in that case, always this methyl signal must be the same if it's the same compound. So you don't have to look at, or you cannot look at all the signal, but this methyl signal is very important. And also supporting cases, sugar, of course, sugar part you can detect it. Sugar part is detected. Phenylpropanoid, another one is peer synthesized, what's that, schemic pathway. Phenylpropanoid, its very name is straightforward. Phenyl means benzene, right? And propan means C3. So that's why C3, C6, and C3 compounds. This is a phenylpropanoid. Phenylpropanoid is after phenylalanine ammonium lyase. Yeah, after that, the first compound is phenylpropanoid. As I told you, what are the essential oil chemistry is monoterpene, sesquiterpene, and phenylpropanoid, but not all the phenylpropanoid. Let's look at this one, saffron. Yeah, saffron from saffron. This saffron, this one is very known for the it can be part of essential oil. But this case is sugar, quinic acid is here, and this one cannot be essential oil. So that's why non-polar phenylpropanoid can be essential oil. So C3 carboxylic acid, usually this 1, 2, 3, they exist as a carboxylic acid, like this one, carboxylic acid. But it's not always, but mainly this one, caffeic acid is here. After caffeic acid, quinic acid conjugated here, is the word quinic acid here, we call it chlorogenic acid. Which plant has a higher amount of chlorogenic acid, caffeic acid, those two are main or ubiquitous phenylpropanoids. In any plants, in the leaf or plants, they contain this one. So that's why some people believe this chlorogenic acid maybe is the precursor. Plants store this one to synthesize tannin or other big molecule bases. Always they store this one. So that's why even though secondary metabolites, specialized metabolites are specific, but this chlorogenic acid, carbonic acid, is very ubiquitous. Any plant contains chlorogenic acid because there must be some, they play a common role. And this chlorogenic acid basis, which plant has a high one, although it's a ubiquitous, but some plants, two plants contains a very high amount of this one. Which one? Coffee. That's very nice. Coffee and then coffee is best friend. No, not best friend. It's a rival. Tea. And also another one, tea. Mate also. Mate is Illes Paraguay's, and also Chinese tea, they contain similar. But it's strange, right? Because Chinese, several thousand years ago, they found the tea, yeah, to be refreshed, right? Yeah, tea and coffee and chlorogenic acid. Sorry, the tea, chlorogenic acid, and Paraguayan Indian, they found the mate. Also, and other compounds, other plants. Africa, they found colada also caffeine. But interestingly, when caffeine containing plant material, I don't know the answer, but this chlorogenic acid always as a counterpart we have a blood. Tea, caffeine is higher, right? Chlorogenic acid also higher. And coffee, caffeine is higher.
Green coffee.
Yeah?
Green coffee. No coffee. As chlorogen.
Sorry?
Chlorogen can have more in green coffee.
Green coffee. Yeah. Green, what I mean is coffee bean, this is very high, and caffeine is high. I think maybe there is an interaction, but I don't know. But as he mentioned, coffee, we cannot drink a green bean, right? It's always roasting. Yeah. So that's it. Depending on the roasting, taste is completely different. Then this chlorogenic, as you see, is the one is very weakly cleaved. But sometimes some people say, when I drink a coffee, I have some stomachache, right? Stomachache. It's not because of caffeine, usually it's because of this chlorogenic acid, they say. So that's why, depending on the roasting, maybe there is some effect on the stomachache. Of course, you cannot sleep while you are going to open toilet. It's because of the caffeine, but stomachache, the stomachache is chlorogenic acid. And here, this caffeic acid in animal spectrum, one of the easiest method is caffeic acid detection is in animal because those two signals, although this one is a double bonds, olefinic proton, but they are very downfield shifted. 16 hertz, you can detect it. This one is a fingerprinting of the plant material to detect chlorogenic acid, caffeic acid. But this caffeic acid, usually under the light, or if you keep longer, this one is cis form or transform? Transform, right? When you keep long time in the solution, they become automatically cis form cases. So that's why when you want to detect your plant material, what stops, whether this one is fresh or not, always how much the ratio between the transform and cis form. But this transform coupling constant is a 16 hertz. But cis form is a 10 hertz. So that's why in animal spectrum it's very easy. Of course, mass spectrum, trans chlorogenic acid, cis chlorogenic acid, trans caffeic acid, cis caffeic acid. The slightly different of detection type. We can detect it, but animal is more obvious. And here, now is dicaffeic acid is fine because first chlorogenic acid, another chlorogenic acid is here. We call it dichlorogenic acid here. Now, here there are two sets of this group. Look at here. There are two sets of this group. Now here, smaller. This one is cis form. So that's why when you are doing very fresh sample which contains chlorogenic acid, polypropanol, you can detect only 100% this one. But this one is after keeping long time, it increase. Now you can test your coffee by animal. I don't know whether it's allowed, but anyway, this one is you can have a look. And still value. Have you heard about still value? Still value it means C6, C2, C6, 1, 2. But it looks like, then how about, why this one is C6, C2, C6, 1, 2, 3, right? It can be very proper. No, it's not true, because this one, in terms of biosynthetic pathway, after C6, C2, additionally, phenyl is attached in based on, if you ever experience, you can easily recognize. But usually, still value, like of any propanoid cases, mainly C6, C3 is okay. Yeah, but still value cases. Now C6 after then additional phenyl is attached. One of the famous one is what's that? Resveratrol. Yeah? From where? Red wine. From red wine. Some people say it's resveratrol has some health benefit, so that's why they are. Yeah? They have a nice excuse every day drink bottle of wine. But some the toxicity test or some in vivo or in vitro test still is a debating question whether this resveratrol is really health benefit or not. Because if it's really working, you have to eat a little bit resveratrol. But in the red wine, the content of a resveratrol is very tiny. If you want to drink resveratrol through wine, of course you will have at the end have a health benefit. Before that, you will die because of alcohol. This is a problem. So now no trust. This resveratrol cases now you can detect. Yeah. And legal none. Sometimes some people confuse what's the lignin and lignin cases. Lignin is a lignified, the soluble material from the batteries. Actually, chemical structure is a polyphenol, old one. But lignin is a small molecule, is dimeric, pennypropanol. C633 and another 633, they are oxidative properties. Like this one is formation here. This one and this one. So this one is a lignin cases. And this one, another here, sesame, and another this one. Now you can recognize, so that's why the direct version of the lignin cases, two compound, but this pennypropanoids coupling position is very tricky. The beta coupling case, but some kind of there is an exception. And here now is the sesame. Where is sesame oil? And podophyllotoxin is a podophyllo. In the old times, one of the most famous natural product which has an anti-cancer activity, podophyllotoxin. It's like a sesquiterpene lactone, it was banned because it's too toxic. As she mentioned, it's not selected. But the Swiss company, they semi-synthesized after isolation of podophyllotoxin. They treated some change in the functional group. They found it etoposide and leukocyte. They are still using for the leukemias. So one of the successful stories to develop a new drug from nature is podophyllotoxin being used, and leukocyte, etoposide. Here. Then now I told you yesterday. You heard it. Now you heard it. What's that? Stereochemistry, right? Hydrogen center, R form, S form, enantiomer, diastereomorphisms. Usually, in general, in natural product, there is one form, right? But as you mentioned, yeah, glucose only one form. Which form it is? D-glucose. L-glucose is not natural. Right. Amino acids, usually N amino acids are natural. D amino acids is a very rare case. Actually, in the past, we didn't know D amino acids exist. But now, more and more, there are more evidence. Many compounds, they have two forms, like arabinose cases. We believe D-arabinose is the natural form, but now we found a lot of L-arabinose. Galactose cases, we believe D-galactose, but we found L-galactose in nature. But now it's getting changed. But anyway, usually natural drug, they prefer one form. But lignant cases, many cases, they have two or three forms. There were three forms. Be careful, when you isolate the lignin, probably in your extract there is another diester form or enantiomer form cases. For example, many lignin cases, you found it, okay, this compound. Please count it where is my chiral center. Then is there any possibility to have another chiral center? Then if it's chiral center, probably you can check. Of course, enantiomer you cannot distinguish by conventional chromatography, but enantiomer cases, diastereomer cases, you can detect by chromatography. Good news is, bad news, lignin has a lot of diastereomers. But good news is, usually most of the diastereomers of lignin is easily separated by chromatography beautifully. There is no problem. And coumarin. Have you heard about coumarin? Coumarin is kind of a trigon, the pennypropanoid. Now C6, right? And then 1, 2, 3, pennypropanoid, right? After that, now this one is here, then they generated another 3. But this one is oxygen and ketone. What's the name of this one? Lactone. So that's why pennypropanoid lactone is a coumarin. This coumarin is you have experience with it's a very fluorescent compound. When you do TLC in the extract, under the UV light, it's very fluorescent, like a star in the sky. Yeah? Steady star in the sky, this sky. And even without TLC, you can recognize. When you extract it, you believe this one contains coumarin or not. Under the light, please look at your test tube. It's fluorescent. So it's okay. Now you are target chromatography. You want to separate the compound. You fractionate test tube. Yeah. Now you are waiting for the THC or some analysis. But if you want to see a fast screening test, please put the line on your test tube. Some test tube which contains a high amount of coumarin is a very fluorescent. It's very easy. This coumarin is this now. Now it's additional, but be careful when you do this one, when you do extract with a strong acid or some acid or alkaline, this one easily cleaved. So that's why now this additionally with the acid, if you extract the acid or the alkaline, basic solution, then they lost this thing. But fortunately, when you return to normal pH, they regenerated this one, but not always this one. And what kind of compound is it? Usually, the prostacine, cruciferide plant material contains high amount of coumarin, particularly umbelliferol. Umbelliferol is the most common plant material. Is umbelliferol, or if it's one OH is here, aspartame. Aspartame cases, aspartame. And if aspartame contains another sugar, glycoside of coumarin, we call it aspartame. Aspartame cases. Those three, so umbelliferol, aspartame are the most common coumarins in plant material. But it's not only coumarin. Dicumarol, anticoagulant, which has been used for the killing mouse, mouse. And then novobiocin, one of the famous antibiotics. This one is from coumarin. Where is it? This coumarin. After this coumarin, there is additional 1, 2, 3, 4, 5. This one is, which means this one is. Please look at this structure. Is it pennypropanoid? No, it's not pennypropanoid. Why? Because here, 1, 2, 3, but additional 2. It looks like a C5 unit, which means now you can guess. After coumarin and penyl is somewhere C5 unit, which is used for the terpenoid, is attached. Now, based on structure, scientists always guess precursor of the compound. Now, this one is sugar, after sugar. Now, first coumarin, and then phenolic, and C5 unit. Now you can read it now. And this one is coumarin, another coumarin, they coupled. So that's why some people, if they don't have any biosynthetic pathway, they have always problem. What kind of group it is? Yeah, is this one is terpenoid or not? Always when several precursors mixed up, please look at the center. So that's why this one is classified not hemiterpenoid, but this one is classified as coumarin cases. You understand? I think I shouted a lot. Huh? Let's calm down. Any question?
Marine is basically is more common in crucifers.
Yeah, but it's not always. If I say, as I think I talked to Major in the last yesterday in the break time. The most dangerous thing in the science is experience. When I say experience, it's not always true. It's in my experience. Huh? In my experience, but it can be. There are other plant material, but cruciferide, umbellifera is very common. And any other question? Huh?
How do you identify the center of the molecule so you can differentiate and between coumarin and the
Now, is for example, this one is when you learned it, you might have a question. Now, this one is sugar, right? For example, sugar moiety. This one is coumarin moiety. This one is vanillin moiety. This one is a C5, terpenoid moiety. Then I said this one classified coumarin cases. Yeah, coumarin cases. But she said, how can I? This one can be sugar derivative. This one can be vanillin derivative. This one can be terpenoid derivative, right? How can I distinguish?
Complex?
Huh?
By the most complex.
Most complex? Yeah, this is but I don't have a gut feeling. There is no rule, classical rule. There is a question is, usually primary metabolite first listed out. Primary metabolite, sugar, or sometimes amino acid conjugated possible. When they attach in the secondary metabolite, please ignore from primary metabolites because it's a later synthesized. So that which means sugar is not. This is clear. Now this one. And among this one, there is some priority. Phenolic part is the main one. Terpenoid listed out, right? Then there are two parts is left. Which one is complex? As she mentioned, coumarin is the complex. And also you can guess. After coumarin is after vanillin is attached to coumarin, or after coumarin is attached to vanillin. Nobody knows it. In that case, you may choose it more complex structures. This is more or less. There is no general rule, but if you exercise it yourself, probably you can classify. Or sometimes you have a different opinion with the expert, but it does not mean you are wrong. Always debating question. Like a taxol cases, after diterpenoid, nitrogen attached. Then many people, in terms of biosynthetic pathway, this one must be classified diterpenoid. But some people say, no, alkaloid nowadays in modern science, alkaloid is classified nitrogen containing, any nitrogen containing compounds. Then taxol must be alkaloid cases. But now it's diterpenoid alkaloids. That's why there is no golden rule cases. But usual general one I already explained. Is that okay? Any other questions?
You have one problem with this compound because you had a methyl group at the four position. Maybe it came out.
This one?
No, in the four position.
This one.
Yeah. It's maybe it's skin came from acetate pathway of the coumarin or not. Maybe it's acid methylation. I don't know.
This one is a very
What complicated problem?
This one is a very complicated
Yeah.
question. First one is, I'm not expert, but this case here, 1, 2, 3, 4 position is methyl group is a key form. Usually plant coumarin, they don't have a 4 position methyl group here. Methyl group here, but if the coumarin synthesized from microorganisms, they are often have this methyl group, but so based on this one, based on isotope experiment, although final product of coumarin from plant, from microorganism, they are same, but they are precursor. They think it's different. Microorganism cases, they are synthesized from acetate. Plant cases have the phenolic shikimate. So our product is the same, but production way is different. But this is a little bit advanced one. But this one, I guess, is acetate cases. Yeah. Here, this one is a micro, because longobiosin is synthesized from bacteria, Streptomyces. This one is from, probably, this one is acetate. C2, this one. But plants, usually they don't produce this C2 They first made this aromatic name and put another. This is the shikimate. This is clear. So that's why now is you learn it. Same product. Sometimes the way to be synthesized in nature completely different. Not only organism itself. Do you know? Now it's terpenoidal synthesis. There was a long time debating question. One of the precursors in the old book, they said metabolomics technique. Right? You heard it probably. But now there is a new book, there is MEP pathway. Then two groups, they are fighting each other a lot. So terpenoid in plants, they are synthesized through metabolomic pathway. But some people say, no, it's not metabolomic, MEP pathway. They are fighting each other. But do you know what's the conclusion? Both are possible in plants. Some plants use metabolomic. Some plants use MEP pathway. But even same plants, depending on the situation, sometimes they change the biosynthetic. There is a very flexible basis. Yeah, that is so there's no fixed model, fixed precursor, but what I explained in general. So that's why always scientists should be open to other possibilities. Always the other the barrier, to flow your open character is your experience. I experienced can be translated by someone I know. And actually I know, it's very little I know, very little it should be open. Here, now coumarin cases, this one is third bond, this one is cis position, always is a pentase. Now, if you learn animal spectrum, as I mentioned, progenic S16 has, this one is pentase, very characteristic marker signal animal spectrum for coumarin. If you measure this spectrum, now it's around 6 ppm, 10 pence and by compounds, the microspectrum contains coumarin cases. That's one of the power of animal spectrum. Mass spectrum, you don't know which class it is, but animal cases, based on this one, you can recognize. And flavonoid, the queen of the secondary metabolism. Flavonoid means C6, C3, C6. Based on this one, what's the precursor of flavonoid? C6, after phenylpropanoid generated, and then additional phenyl group is attached. So that's why still. So which means Now you realize which one in the biosynthetic pathway, which one is the first? Phenylpropanoid and then flavonoid. So that's why if you upregulate the phenylpropanoid cases, actually phenylpropanoid cases, probably it influences a lot in the flavonoid. Even based on only one information of this one, this one, you can recognize all the biosynthetic pathways. Basic one is there are many sub flavonol, flavonol here. 1, 2, 3, 4, 6. 1, sorry, 1, 2, 3, 4, 6. 1, 2, 3, 4, 1, 2, 3, 4, 6. 1, 2, 3, and additional very C6, C3 compound. So there are, this one is a complex biosynthetic pathway, combined biosynthetic pathway, flavonol and chalcone. Chalcone, right? Chalcone cases. Here, 1, 2, 3, right? After that, addition. So, chalcone cases. So, chalcone is in the biosynthetic pathway. After phenylpropanoids, you attach, phenyl group attach here. Phenyl group attach it here. Then this one is the first flavonoid synthesized in nature. After that is a ring closure coming. This one, and this one. Right? After that, dihydroflavonol, there is no double bond. And usually number one, two position, number two position is attached here. Sometimes different. Phytoaldehyde. In the first stage, I already explained. Yeah, if plant material, bean, particularly bean sample, yeah, like the kidney bean or PCM sativum, when they are infected, is isoflavonoid increased a lot. And also, this one is the famous now. You heard it probably. Phytoestrogen. Do you know phytoestrogen? Yeah. Which one is phytoestrogen? Phytoestrogen is digoxin or genistein. Yeah, genistein, which are very common in bean sample. So that's why in soya sauce, in Chinese soya sauce, or in tofu, you know tofu? Tofu, they contain a lot. Or soya milk. Soya milk, you have a lot of these compounds. Phytoestrogen means actually phytoestrogen is isoflavonoid. It does not look like estrogen. Estrogen is a steroid hormone, yeah, for the ladies, for female hormone, yeah, for sexual mature reason. But these estrogen cases, yeah, when they do 3D structure, someone said it is isoflavonoid, the diazine, while genistein looks like yeah, similar as by estrogen. They they are they are sometimes playing a role like estrogen role. So that's why some doctor, I don't know whether it's true or not, some doctor they don't recommend young lady before menstruation, young lady to drink soya milk because if they drink too much soya milk, it's already sexual maturation happen. Probably they start too early of menstruation phases. So that is a isopropyl. But mostly it's in product. Okay? Now it's catechin. You heard it? Catechin. Which plant has a high amount of catechin? It's everywhere, but usually tea. What? Caffeine? No, I don't think this catechin is very common in coffee. But usually tea has a high amount of catechin, very bitter taste. Yeah. And anthocyanin. You see, anthocyanin is a very rare compound. After that, now it's number one is flavonol. Number two position. Number three position isoflavone. And number one, two, three, four position we call it neoflavone. Neoflavonoid and alkaloid. This one is a very soft of neoflavonoid. That's a debating question. Whether this one is flavonoid or lignan. Many people, I don't know what's the conclusion at this moment, but this neoflavonoid, but in terms of the structure, it belongs to flavonoid, neoflavonoid. One of the famous compounds of neoflavonoid, probably someone knows? No? Brazilin. The compound name is Brazilin. I think it's one of the medicinal plant from your country. This Brazilin shows very high antidiabetic activity. Neoflavonoid. And you will, uh, that is a very difficult question. When plants produce secondary metabolite, protein, flavonoid, or terpenoid, second step is the attention to sugar. We call it the glycoside. Yeah? It's called glycoside. But this glycoside formation always, I don't know why, there is a very specific sugar, like iridoid cases, they only attach with the glucose. But flavonoid cases, there are any kinds of sugars like galactose or arabinose, glucose, no problem. Tripropanoid also no problem. But as you see, caffeine, methylpropanoid cases, very specific sugar, quinic acid attached. And which means maybe they are present in the same location, synthetic site. But flavonoid cases, additional one is additional effect is generated. Flavonoid, sugar to the sugar, sometimes you know it, the organic acid, like malic acid, or sometimes phenylpropanols, like caffeic acid, they are conjugated to sugar. So that's why when you look at the phenylpropanol, the glycoside, phenylpropanol, sugar, flavonoid, sugar attached, and other acid compound is a three-part is there. So now, then this one is, whether this one is sugar or organic acid, or flavonoid, as I told you, it's flavonoid because it's a most complex one. Then why? Nobody knows. Why? This acid conjugation to the secondary metabolites is only flavonoid, but there is some guess. There is some guess. First guess. Why flavonoid prefer last acid conjugation compared to others? Have you thought about that one?
Never think about it.
You can think about it. Because always from textbook you learn, but textbook is not correct. But you have your own question. Now that I think of it, it's a good question. Maybe flavonoid is the usual storage places is a vacuum, right? Vacuum contains a higher amount of acid, and vacuum pH is very low. To accustom their structure, probably they need additional acid, or the other way around, because they are in their environment, they have a lot of acid, yeah, to store that one acid conjugated, automatically conjugated. I don't know whether this conjugation is for some purpose or whether this conjugation is because of environment. But anyway, one of these cases. But important one is acid conjugation never happened in saponin, only flavonoid cases. So message is first one is glycoside, glycosation, sugar attachment. Yeah, there are preferable sugars. Second one is glycosation is not last biosynthetic pathway. Sometimes additional one is attached. That's it. It's like a building block. It's like a building block. Sometimes you start with a very nice Lego. You made it one. You made it one. Why not? You put together something. Is that answer to your question? And although nowadays is very important one. So that's why yesterday I was introduced to your SMS part, SMS tutor part. But many people they say, oh, if I have a mass spectrum, we don't need a UV spectrum, DAD, yeah, DAD spectrometer. No, it's not true. For the natural product, always UV spectrum is better. Sometimes UV, the mass spectrum, is not distinguished, but many phenolic compound based on UV spectrum is possible. For example, this one is gold method, flavonoid cases. You can find it here. Now, flavonoid cases, always, there are two bands coming out, 250 and 360, more or less, this one. It's a flavonoid case. But isoflavone case is only one. It's like a tops of a camera, yeah? Two tops or one tops case. So based on this one, you can recognize whether this one is a flavonoid or not. I adopted from very old book. Sometimes in the old times, when I first submitted my first paper in 1996, probably many of them was already, is not yet born. But anyway, and then 1996 paper, when I submitted my new compounds of flavonoid, yeah, flavonoid, then the editor asked me, please shows all UV spectrum, even not all UV spectrum, to know the position of OH. You need NaOH, NaOMe, more aluminum oxide, those kind of chemical reaction, you need it. That was the rule. But nowadays, you find the new flavonoid, you don't have to do. Because now it's a mass spectrum, and NMR is already very nice to distinguish mass spectrum. You don't need it. But all the time, you need it. But it's all the time method. It's not necessarily to be, you have to abandon. You can use it if you have a UV spectrum. That's why I added it. Yeah? So that's why this UV spectrum now is UV, the flavonoid UV spectrum very characteristic, which means always I claim my hypothetical assumed role of flavonoid. Maybe, flavonoid can play a role for the as a sunglass of plant UV protection. So that's why now sunlight gave a lot of diverse UV land, UV land. But plants, they should have a own preferable UV the wavelength, right? Based on this combination of flavonoid, maybe they have some filtering effect of this in the for the role. And also another example is maybe there is a rumor, you heard it, ginkgo biloba. Yeah? Ginkgo biloba. Ginkgo biloba is a kind of a fossil plant. It's a very old time. And someone said even ginkgo biloba survived in the nuclear weapon in Hiroshima because they have own flavonoid better. They protected those kind of radiation cases. This is one of the examples. And also another example, some botanists or ecologists, they found the same species but different altitude. Different altitude is the lower altitude. And top of the mountain, most very metabolic group is flavonoid. Why? Because it's clear. On the very low land, there is less UV radiation from sunlight. But top, they have a very strong UV radiation. Based on this one, probably flavonoid is one of the role of flavonoid. And flavonoid basis, many people, now you heard it, antioxidant, right? Many people, they claim antioxidant, but for me, I have a bit down. If you have in the nature, half of them has antioxidant effect. As long as they have a phenolic OH, they have antioxidant effect. So that's why flavonoid, they always say, oh, it's antioxidant, or it's good for your health. But when you isolate the compounds flavonoid, they never show the strong activity, always mild activity. It does not mean it's useless to develop a new drug for plant. Instead,
was thinking maybe flavonoid can be a synergistic effect. Together with other compounds, maybe flavonoid shows some effect. One of the good example is in Korean drug development. You know Artemisia. Yeah, Artemisia. It's not Artemisia. There is eupatorin. In one of the species of Artemisia, eupatorin was found very flavonoid and very methoxic, many methoxic group. This eupatorin itself, there is not much activity, but together with omeprazole is a very nice activity against the, Helicobacter is omeprazole plus this eupatorin. So nowadays in Korea, there is a quite high number. So to develop a new drug, it's not only single compound which shows a high activity. Maybe we have to change the paradigm. It's kind of synergistic. Actually, it's not this course, but anyway. The UV shifted reagent. This one is I used. The reason why I added this one is old-fashioned method, but you can have some idea. Maybe when you are reading new paper as an old paper, you can read it. Why you can understand why they used this one. Animal spectrum. Nowadays, animal spectrum flavonoid. Or mass spectrum is more than enough here. Now it's typical example. This region I told you, progenic acid, coumarin, and flavonoid is very important region in the animal spectrum. It's more fun. Why? Because it's two heads. Flavonoid. Of course, you don't have to understand right now, but please keep these slides for the future study. This one is fingerprinting way to find the compounds. And now naringerin, where is it from? The grapefruit. The grapefruit, because of bitter taste of lemon. Lemon is a sour and bitter taste, right? Bitter taste of lemon is limonoid. It's kind of a terpenoid. But grapefruit, so like a big orange, grapefruit bitter taste is from naringerin. Naringerin here. This naringerin is here. Now, this naringerin, glycoside, is glycoside here. It's glycoside. But where is the chiral center? If there is a double bond region of flavon case, there is no chiral center. But if this one is chiral center is here, it's not double bond. This one is a chiral center, right? Only one chiral center here, right? Only one chiral center means this naringerin possibly R4, S4 can be exist, right? But if compound is exist only with this glycol, we cannot distinguish because enantiomer R4 is completely mirror image, we cannot distinguish. So that's why, and also one of our hypothesis is in nature, compound must exist as a one form. So that's why they didn't have any doubt on my thesis. Long time ago, it's 2008. Yeah, I want to make a build of the animal spectrum, a database of animal spectrum. I voted naringerin. Naringerin means this naringerin plus glucose. Plus glucose. But glucose, how many chiral center there? 5. Yesterday you counted 5 or 4 chiral center, right? Now, if you attach the one form of chiral center, only naringerin, R4, S4, you cannot distinguish. But when glucose added, it become not enantiomer, it's a diastereomorphism, which means it can be distinguished in the animal spectrum. So now here, when I measure here, this one must be, when I measure here, must be double, because beautiful double comes out. But when I buy naringerin, glycoside here, two sets of doublet, I thought, or many people thought it's an impurity. Yeah, so that's why this one is 99% impurity. The explanation means in nature there are two forms, I form and S form. So that's the one of the finding I published some food chemistry, some like published. So you learned it here. Of course, in nature, one form they prefer, but it's not always true. That's it. You learned it today. And Vitexin is where is it? It sounds like where? Uva. Yeah, uva. Super uva. So here glucoside, but usually the only problem, it's also another mystery. Mystery is always I'm sugar, but glycoside is here. So it's like when I conjugated always is OH, my OH, we share. So that's why ether bond is here. Or if he is a COH, IOH, ether bond is here. But flavonoid is interesting. It's a CC glycoside here. It's only flavonoid. Can you see it? See, there is no oxygen in the medium. So that's why when you isolate this vitexin, like a C glycoside, if you added acid, strong acid, whatever acid, you cannot hydrolyze. This is another problem. But now, vitexin cases is here. Now this signal, I bought it from Sigma Eldridge, and you measure it here. Looks like this one. What's that? Looks like impurity, right? If you don't have any information. Okay, even I bought this isolate one, probably impurity. I can even know. But the problem is, situation is rotating. Have you heard about the rotating? Rotating means this one, yeah, here, this one is because of here, now is this one, although 3D structure is very close, semi-intra hydrogen one generated. If there is fast rotating, it's very clean doublet is coming out. But because of interaction of this one, because 3D structure, they are very slow rotating. Two forms are generated. It's not because it's an impurity. It's like a Janus, as I mentioned. It's like a glucose cases, rotating. Now, if you know this information, if you know this, it's a very important marker for vitexin compound. But if you don't know, you know it's an impurity case. So that's why NMR is not always source. One form is always diverse form. You learned it, sugar. Today you learned it, iridoid cases, right? Iridoid cases. You learned it, this vitexin cases. Always there are several forms. Yeah.
In this case, if you play with the different solvent and or with temperature, you can
change some ratio. You can change some ratio, of course. Like DMSO cases, probably DMSO cases. DMSO, I think DMSO I could find. Yeah, but maybe it's a strong acid, maybe it's it can help. Yeah, because anyway, the message is they are connected. Yeah, semi-connected. So that's why those two protons are detected here, 2 points. It's because it's slow rotation. Maybe temperature, if you have a high temperature. But now, if you know this one, why do you want to remove these cases? Why you can use it for the structural oxidation, the mixture. And phenol. Phenol means phenol here, double bond, here, phenol. Benzoquinone, this one, naphthoquinone, anthraquinone cases. Yeah? Benzoquinone is usually from microorganisms. Naphthoquinone, maybe not microorganisms, but some plant they have naphthoquinone cases. Anthraquinone, this one is mainly from plants. Any plant material contains anthraquinone. There is one specific activity. What's the activity it is? For your constipation. For your happy life in toilet. Yeah? Laxative. Any plant contains the anthraquinone, they have a laxative effect. But then in terms of structure, what is the problem? It's ketone group. Yeah? This ketone group easily converted to OH. If you keep long time after harvesting, you keep long time this plant material, this ketone simply change to OH. Then now there is a problem. First one is if they change to OH, maybe it can cause toxicity. Or some activity, maybe because of this alcohol function. So that's why when plant material has a high amount of anthraquinone, always there is a description. you have to use this plant material after harvesting within 1 month. It's because of kinokis. Or some plant cases, they have this prediscription. You have to use this plant material after 1 year storage, which means they need a wet space. Always keep in mind. Laxative. Laxative. For constipation. And one of the plants, famous one is rheum species. Like rhubarb. Yeah, rhubarb is a red one. That red one is from Anthraquinum. Of course, this one is not toxic. But Chinese rhubarb, we call it rheum species, R-H, yeah, R-H-E-U-M. Rheum species is one of the famous laxative. So that's why if they have, particularly ladies, they have some problem with the constipation. In that case, they prescribe the treatment is amodine. This amodine containing plant material. Of course, in the beginning, it's working very well. But the problem is, if you are using often, it's not working anymore. Why? You have to be very cautious. You have to be very careful to use this. Right? Why? Because it can change all the gut microflora. So if you add too much anthraquinone containing medicinal plants, in the beginning, okay, it can be very nice, but you have to increase a lot. So that's why it's a little bit. So when the traditional Chinese medicine, they always combine with the other plants. And in terms of activity, amodine is the best for the laxative. And this amodine looks like a pattern. Here. The last big group is alkaloid. What's the alkaloid definition? No, it's a classical definition, what I mean. Classical definition is alkaloid. Heterocyclic. Nitrogen containing compounds. So nitrogen should be in the benzene, somewhere ring, yeah, ring system, and compound from plant, and it should be basic, not acidic. It should be intensive biological activity. And one more, I forgot, it must be synthesized from amino acid. That's the classical definition. But later on, they found it. Some alkaloids does not have heterocyclic nitrogen, only free nitrogen. So that's why they deleted heterocyclic. Some alkaloids is not only plant, it's like Brazilian toxic frog. It's a toxic frog, they contain alkaloid. Okay, let's take out the plant. They take out the plant. And then some plants, some compounds, some alkaloids, even though they have a nitrogen, they are not basic. They are acidic cases, like NHCO. Yeah? NHCO groups. Yeah? Then they take out the basic. And some alkaloids is not always intensive activity, sometimes mild activity, like the verbal cases. Some plants, some alkaloids, they are not from acids. So that's why nowadays modern definition of alkaloid is nitrogen containing natural product, not amino acid, not protein. That's the cases. But why I always ask the student to know this one? This one is the classical definition, which learn what's the compound. And there is no exact definition. It's nitrogen containing compounds, not protein, not peptides, amino acid derivatives. And now, just nitrogen containing natural product, very plant specific. This alkaloid, actually, so although some alkaloid does not have strong activity, but this alkaloid usually have very strong activity, and in other words, toxicity. So that's why many people, when they want to do drug development in all the time, they always focus on these alkaloid cases. Alkaloid containing compound, I like it very much. So that's why it's quite strong. Activity, bioactivity, it can be strong toxicity cases. Always is mutual interactive. And this one is pyridine. So in alkaloid subgroups like a flavonoid, flavon, dihydroflavone, or aurol, bisoflavone cases, and alkaloid also depending on these structure, they have several groups here. Now pyridine alkaloid. Here, this one is pyridine. Pyridine alkaloid. Now this pyridine alkaloid. What is the pyridine representative of famous pyridine alkaloid? Nicotine. Nicotine cases. And when you find nicotine, always this one is anamacin. Anamacin. So ornithine and lysine is generally. And this one is synthesized from glycine aspartic acid. And this one is glycine aspartic acid, and this one is from glycine. Nicotine cases, although now is only in the smoking or the cigarette, but actually ecologically it's a very important material. So have you heard about this one? When farmers grow tobacco in the field, you cannot grow any other plant forever. Why? Because they release toxic compound. The other plant cannot grow anymore in those soil because it's nicotine, the nicotine cases. Yeah. It's a very strong plant material, tobacco. I don't think it's Brazil. You have a big farm of tobacco, right?
On the south.
South.
Exactly.
Legally.
Legally.
Yeah.
It's not big farm, but
Okay. This one. And another one is one of the illegal drug. Which one is chocolate, cocaine. Yeah, this cocaine drug is this group of alkaloid. This group is tropanic. So that's why we put the tropan alkaloid. One of them is cocaine. I don't have to mention. Yeah? You know very well from coca, from somewhere from your neighbor. And here's atropine and here's amine. You know, one of the historical moment for natural product chemistry is 1970s or 1980s. This natural product chemistry combined with the molecular biology. There are many groups. It's like a long time ago in Germany, Zenk group, yeah, right? Zenk group or my former boss, Verporte, is interested in the At that time, 1980 or 1990, there are several groups who is combined molecular biology and compounds. Why? Because before that time, we are only interested in the product from plant, but they start to think about biotechnology cases. How plant produce, those kind of, it's mysterious. So that's why they start to think about biosynthetic pathway. There are several groups of plants, model plants. Yeah, Zinc group they are using morphine, opium. They used. Our group, my former boss, Dr. Felporter, he used Catalanthus, indoor alkaloid. I showed the structure. And Japanese group, yeah, Yamata group, they use this atropine compound. Atropine compound in the Solanaceae plant material, this atropine and scopolamine, they are synthesized. Only difference is this epoxide ring, In terms of bioactivity for drug-like compound, is scopolamine. Although nowadays it's banned, this scopolamine is being used as a patch type for the CC. But this atropine is like hyoscyamine, it's still being used in military. When something is a chemical weapon comes, they always bring this one to use for their emergency cases, atropine cases. But they were interested whether it's first, they want to know how do they synthesize. First, they found after atropine, this epoxide ring is added. After then, their question is, can I control to produce more this scopolamine? There are some successful stories. One of the, but not only for the application, this compound is historically valued. Is atropine and scopolamine. Cocaine, political, social, society value. Yeah, no. And another alkaloid, pyrrolidine alkaloid. This one in organic chemistry we call it pyrrolidine alkaloid. What's the pyrrolidine alkaloid? Pyrrolidine alkaloid is not for the not for the bioactivity, for drug-like compound. History original algorithm around in the beginning of 20th century, 1910, or at the end of 19th century, in South Africa. There are several places in South Africa, or some Canada, or somewhere they have a big farm to grow many cattle, yeah, sheep or cow. The one day, without any reason, they died. Yeah, they died. So that's why they say it's surveyed a lot of plant material. Some plants containing this pyrrolizine alkaloid, selectionin or monocrotaline, those kind of compounds, they cause the problem of animal which has a rumen system, not human or cattle, like sheep or cow, not pig, or even the goat cases. So that since then, they started, this one is a model compounds for chemical ecology. Why is model? Because this one is plants usually produce, when they produce one compounds, it's very expensive. For example, one plant produces one compound, they are using, I don't know exactly how much, is 10% of metabolic energy, right? Then which means they want to reduce number of compounds as less as possible. That's for the survival. Interestingly, is senecio containing plants rich in alkaloid in one single plant material, very diverse derivative of this pyrrolizine alkaloids. Then, which means there must be some interaction cases with the environment. So many chemical ecologists are targeting this compound as a model plants. Pyrrolizine and phenolphthalein alkaloid, it looks like this one. But this one looks like taste heater, which means this one is a marketing, while this one has been traditionally used for the bitter taste, which means for stomach. And Indonesian alkaloid here is a very rare compound, You can find it. Benzylamine compound. Is this one is alkaloid or not? True alkaloid? No, because nitrogen is not in the ring. Actually, in all times, this one is not alkaloid. It's only phenylpropanoid. 1, 2, 3. After that, nitrogen is attached. So that's why, in terms of according to the classical definition, it's not alkaloid, but nowadays changing benzylamine alkaloid. Yeah, this one is many enantiomer or diester because there are two kind of center. So that's why the first founder or discovery of stereochemistry, who is it? French scientist Pasteur. Right? Pasteur. After that, in the beginning of the 19th century, from the natural product, they want to study stereochemistry. This ephedrine is being used for the model plant by Japanese scientists. It's one of the historical compound. And for the activity, this one, ephedra plant material, which contains this ephedrine plant, has a anti-asthma, but it's been used, so that's why it's been used a long time. It's a ephedra containing plant in the for the drug of cold. Yeah, drug of cold, they used a lot, but it's ephedrine banned because there is many toxicity comes out. Instead of ephedrine, there is additional compound, different enantioxidant, diasterol, pseudoephedrine they added, but it's also toxic, it's banned now. But still, this one is being used where? Do you know? In the illegal dietetic product. Because if you buy some diet food from the internet black market, they added this ephedrine or ephedrine horse. Why? Because it's anti-appetite. If you ate this one, you don't want to eat anymore. So that's why be careful, yeah, this one. And also this one is starting off precursor for what? Some drugs. Your rival, Maradona, was accused in 1994 in the American football, yeah, World Cup competition. copper, because he took it this one. What's the compound it is? It's a derivative of this compound. Amphetamine is from this compound. And isophenolene alkaloid is a phenolene alkaloid or piperidine alkaloid. Piperidine alkaloid is being used traditionally for the what's that for the anti-pesticide, anti-parasite. Because nowadays, no problem, you can take a pill from the synthetic compound, sanguinidine or this one. In all the times, it was a really big problem, because hygienic cases, they use this containing arecoline cases. And arecoline cases, what is arecoline? And also, you heard it, some of South China or Southeast Asia, like Malaysia, Taiwan, or Indonesia. Have you heard about Vietnam? Many hard worker like a taxi driver, truck driver, they eat some red fruit. Red fruit, they call it Vietnam. It contains alcoholic cases. It's a kind of narcotic one. And when they take it too much, your teeth become red. And also, when you travel, something is Southeast Asia, like in Taiwan, whatever, they, after taking this one, they spit on the street. Then it looks like a blood, but it's not blood. It's because of this one. That's the main compound. It's from arecoline cases. And indoor alcohol is one of the famous now by study from tryptophan. And after making tryptophan, and they added indoor, like the terpenoid, secoid, logaline cases, we call it indoor alcohol. Vincristine, vinblastine, and yohimbine is very toxic. Vincristine, vinblastine is still one of the famous successful stories from natural product like development and cancer agent. Leukemia still is being used, and yohimbine is also very similar compound. It's being used for the mating. It was used actually for mating of pig. So that's why I don't know whether it's true or not. It's yohimbine. Someone said it's included in the black market natural Viagra. Sometimes they say that sometimes this. And nicotine cases here, nicotine, you can find it. And trigonelline. It's a very, usually the alkaloid is very specific, but trigonelline, pyridine alkaloid is very common in solanacea, even including cannabis. Cannabis is not solanacea, but you can find it, this trigonelline everywhere. Most cases, alkaloid is very specific. And this one is indoor alkaloid, tryptophan, you find it, this pattern. And arecoline, you see, very beautiful characteristic signal. If you find the red fruit, from Taiwan, don't take it, just don't take it, but just bring it. Probably you can do mass spectrum or animal, you can find these arecoline cases. And last one is really last, glucosinolate. I told you one of the famous model is the compound ecology is pyrrolidine alkaloid, urine cattle compound. Second model is glucosinolate. Glucosinolate means this compound and plus sugar. I told you glucosinolate sugar is only glucose. There is no other sugars. But instead of OH, sulfur. This one is a sulfur compound. This sulfur compound is a very rare case. In natural product, most cases CHO. Some cases sulfur, like garlic cases, garlic or allicin or allicin cases, garlic cases. And this one is sulfur compounds. And this one is sulfate, is conjugated here. And this one is in brassica species, same as pyrrolidine alkaloid. To produce one compound is very expensive for plant. Why? Brassica plant, they produce very diverse kinds of this plant material. So that's why they believe maybe interact with the diverse spectrum from environments or pathogen cases. This one is, you can find it here, this H, very characteristic. Usually coupling constant of ether bond is 8 or 7 habits. But this glucosinolate, you found it is 10 habits. So if you find the 10 Hz doublet around here, you can assume this one is glucosinol. It's a very fingerprinting case. Of course, one another Vitex case is a C glycoside, also glucose, yeah, not like other one is 10 Hz. But C glycoside, glucosinolate never be in the same plant material. So if you find the one plant material, 10 Hz, 10 Hz, glucose signal, it might be glucosinolate, either C glycoside. And cyanogenic glycoside is one of this one, the CN compound here. From where? It's from the seed. From the seed, cyanogenic glycoside. From the seed, it's like a peach. You know peach? Peach, you are eating the fruit, flesh, yeah? But inside, you are not eating. Goes inside this one, because this one is ecologically there is explanation. I plants gave a fruit, to the bird, or to human. Please eat my flesh, but do not eat my son in the seed. So that's why it's a very toxic compounds inside of this one. If you eat this one, there is some it's not a leather dye, it's a leather post, but it will be a problem. So that's why it's a toxic compound. But there is an interesting story. Do you know macadamia? Macadamia, wild macadamia in the seed, they produce a lot. Because now we are eating seed, macadamia, no problem. Yeah? If you have a macadamia, probably it will pose a problem. But when they are cultivating macadamia, they don't produce this cyanogenic glyphosate. Why? They don't have to protect it because human always doing my job for ourselves. So that's why wild macadamia or cultivated macadamia is cyanogenic glyphosate. It's completely different. One of the amygdala is quite common compound. Why they put the cyanogenic glyphosate means when you are hydrolysis, HCN, yeah, cyan gas, yeah, coming out. Of course, if you inhale cyan, you will die, but it's not that much. Okay, any questions? Sorry.
Let me use the microphone, please. Okay, you have a coffee break now. Then you return in 30 minutes, okay? And person from uh, YouTube, please return again in 20 minutes. And at the end of the class, then we have a question for you all, okay?
I'm afraid it was a little bit. Hmm? Okay, yeah, we can. I hope it's not. It was not so boring for the basic phytochemistry. But why I gave a detailed lecture for this one? Because you have to know the target compounds. Otherwise, we cannot do. You are doing for the all metabolites. But then, what are the all metabolites? So that's why I gave some extensive presentation for that course. I hope you understand. But now is a real metabolomics, starting from sample preparation and also with the extraction. Many people are interested. Most of people are related to plant science here. But for this sample preparation, I included also microbial and human metabolites cases. Depending on the sample, there are different sample preparation or extraction steps. So metabolomics, yeah, sample preparation and sample analysis and data mining. Those three, maybe if I reduce the step, those three steps. So sample today is a sample preparation step, including extraction. So metabolomics cases, what is the metabolomics? You learned it, yeah? What is the metabolomics? Is to know all about metabolites. It was clear because in the beginning of yesterday, we already discussed. And metabolic profiling, you heard the same name, similar name. What is the definition of metabolic? Of course, the definition is a definition. Sometimes there is no clear cut between a definition. But what is the metabolic profiling? What's the difference from metabolomics? But nowadays, any kind of profiling technique must be integrated or hyphenated with other methods. I think profiling itself and metabology itself, they are also connected to other molecular biology or others. But metabolic profiling usually is not for targeted one, but not untargeted one. Certain groups you are doing profiling. So they said, of course, there is no clear. But for example, now you learn the grammar or lipid, yeah? Then lipid, if you target it on lipid group, probably it can be the metabolic profile. It's both lipid or metabolic profiling of grammar, metabolic profiling of androgen. Yesterday, Anitya mentioned she wants to know what's noise and androgen is. Probably it's kind of a metabolic profile, but there is no clear confirmation. And third one is metabolomics. What's the metabolomic? Many times you met this metabolomic. Metabolomic is same as metabolomic, but always medical doctors or clinical study, they want to be different from us. Yes. That's why they use the metabolomic. Usually metabolomic is not often used. Metabolomic is included in metabolomic, but in the beginning they use metabolomic for toxicology studies. Metabolomic in toxicology, in clinical hospital, clinicals or hospital cases. But nowadays, yeah, there is a combined, it's being used by metabolomic cases. But actually same meaning. And metabolic fingerprinting. Because the metabolic fingerprinting, yesterday I mentioned, it's targeted on separate whether it's we are not interested much in identification, but whether it's the same or not. So now, if you do orange metabolomics, Brazilian, Florida orange metabolomics, if the first fingerprinting A is whether your Brazilian orange, whether they are different from Floridan orange one, that is a fingerprint. And what's the footprinting? The double footprinting? Yeah, that's is correct. Metabolic fingerprinting means it's a resistant, it's organism itself. But as he mentioned, it's a secretion, release metabolites. For example, if you have microbes, instead of whole body of organism, if microbes release to the medium, that's the metabolic footprinting. Or even marine organism, yeah, instead of body itself, if they release the metabolic footprinting. But if I define each items for its definition, but there's no place. Sometimes some people say, okay, now I'm doing metabolic, but they identify only 10 compounds. Is it fingerprinting or the profile? We don't know. So there is no clear about, but 8 is a little bit different. But in any case, metabolomics, including fingerprinting plus identification, both either side is very important. Then metabolomics is biofluid, urine, blood, plasma. And metabolic fingerprinting, cell plus microcellular metabolite, and extracellular metabolite. And samples for this, so always we need this kind of sample. Mammalian tissue fluids, this kind of urine is not orange juice. Yeah? So orange, this one is another cases. Microbes cases, there are two kinds of sample, excreted one in the medium and sample, yeah, sample itself. And food, this one. There are many sections. But depending on the sample, you have to use proper extraction or sample preparation method. That's the aim of this lecture. And on a right why on a right of course, if you have one single method, you don't have to be worried. You only one single preparation method. But if you are doing GCMS, if you are doing NMR, LCMS, or IR, so based on part of metabolomic tools, you have to optimize the sample preparation business. Do you agree? We cannot prepare the sample following the animal tools for HMS1. HMS, animal is completely different. Always, animal is rather, we don't have to filter, right? Sample, the sample is like a spectroscope, physical contact, but mass cases is a chemical contact, always a sample should be filtered before injection into the acid. You have the membrane filter. Animal cases, water centrifuge is more than enough. And sometimes it's a throbbing sample. We can measure it. So that depending on the sample preparations are different. And let's start with the most interesting, the plant metabolomics. So sample preparation is first, keywords, all intact metabolites, right? Because I'm interested in metabolites itself, the products. And avoid metabolic degradation. If you have a very long time procedure, probably there's a many chance, very much chance for the metabolites to be degraded. So that's why simpler is better. And also, metabolomic itself, or people thinking itself, you are handling hundreds of samples. You have to think about the time. If it takes 1 hour for sample, now we have 1,000 samples. How long does it take? 1,000 hours. That's why you have to always consider time and efficiency and sensitivity. That is very important. And second one is the simpler is the better. This is very keep in mind. The simpler is the better. And simpler, why? If you have 100 of steps, it's very difficult to keep the robustness. But if you have one step, it's very easy to keep the robustness. This is why simpler. And also it takes more steps, there is more chance to be degraded.
Sure. And another thing that we must consider when looking at race, the simpler is better. The simpler is the better and it's more strong from the point of view of the analytical tools, because if you have more and more steps, the chance of the error propagation
Yeah.
increase.
That is correct. Because each step has some error bar. So if you have a 10 step, then you have a 10 steps, 10 step chance to lose your sample. Actually, each step you will lose the sample. One step you have only one time to lose your metabolite. But if you have a 10 step, each step you lose the sample. But keep in mind, we are doing all metabolites present in the organism. So this is the level. And also metabolites is there is a specific place. Blood, some like volatile cases, they are located in epidermis. So actually, when you do extract the volatile, just to soak in the sample in chloroform, hexane is more than enough. Or even the headspace method is okay. But flavonoid cases, they are located inside the jaw. Or in vacuole cases, you need to crush or rupture the matrix. Otherwise, it cannot be extracted. So depending on the location, the metabolites in the organism is not just a mixture of the compound depending on the location, the extraction efficiency, completely different. But my experience is when you extract it with the ultra purification data, then it's a first, now you extract it first, and second experiment with a certain time, then how much extracted in second time? It's always the first extraction is 90% are extracted. But 90%, okay, I want to get 100%. But actually, you have to sacrifice some time. So now it's 100 the first sample, you extract 90%, always 90% I prefer to do. But if you do sometimes 9%, sometimes 10%, it's a problem. So then your robustness is very important. And sample preparation step is first. Now you think about, as I mentioned, your topic is imaginary topic, Brazilian orange. There, you have to go to harvesting. Harvesting, shock freezing. Why we have to do shock freezing? Okay, now everyone is shouting, which means you know. Shock freezing. So yesterday I suggested a kind of a shock freezing. What kind of shock freezing was it? Liquid nitrogen. Because any kind of a touch, human touch, whatever touch is the plant, accepted free plant, consider that they are attacked. So that's why metabolites are changing. So metabolites changing always is intermediated by enzymes. So that's why enzyme should be stopped. Then shock freezing, liquid nitrogen. But it depends on the sample. And tissue separation. Tissue separation is a very important one. Sometimes you use leaf, but sometimes you use orange fruit. Sometimes you use the fruit. This is different. So that's why tissue separation is not necessary, but always you have to use the same tissue. This is very important. Of course, everyone can separate, yeah, can do separate the root and they distinguish root and leaves. But in each organ, they have several tissues. You have to be very careful. I will show you the example. And dry. Why we have to dry? Most cases, SMS cases, usually SMS mass-based metabolism, they don't dry. Yeah, they don't dry. So they extracted a fresh sample and they added a chloroform methanol and then they take out the organic part, they use the sample. But if you use a fresh sample, what is the problem? Do you expect? Because water content we cannot control. Even you added methanol, but if the sample tissue contains water, this one is not methanol extraction, this one is water, aqueous methanol extraction. This is also a problem. So which means you don't know how much plants is extracted. Usually when you collect the plant material from the normal season, not rainy season, 90% is water. So that's why you collect 1 gram of plant material, only real material is 100 milligram. Even you do freeze dry, it's 10% is water that you do. But that water should be the same. Otherwise, the data is fluctuating. So that's why animal cases, usually we are doing with the drying sample. But drying is, I'll show you, drying is, if you do oven dry, like if you do, burning, or giving a heat oven, all the compounds are degraded. So that's why the best way is freeze dry because we the low temperature. And also freezing dry, another advantage. What's the advantage is it can oxygen or the organ is required because it's a vacuum. Second one, it can rupture the cell matrix because if when metabolized dry completely, they tightly bound the cell matrix. They are not extracted very well. But if you crush the cell, yeah, if you crush it because of low temperature, then all the cell matrix is degraded, compounded, released very well. It's another advantage. And extraction, there are many extraction methods. Oxalate extraction, you know this oxalate extraction and liquid extraction. And this one. But oxalate extraction is with a small amount of sample you have to extract as much as possible. But actually it's not our goal. Always it should be simple and in short time. So that's why we are using another extraction method, simple extraction method with the ultrasonication. And preparation for the analysis, derivatization. You are doing it GCMS, you need the chemistry demonstration and cleanup separation. Sometimes LCMS, now you want to do plant hormone. I want to do metabolic profiling, plant hormone, like oxygen, or ghrelin acid. This is a picomole level, but BP or sugar is very high. In that case, you can apply the solid phase extraction using usually C18 small catalyst powder. But it depends, really depends. No?
Sure. When you consider creating white, for example, material that you find on the outside, like when you bring back the potatoes and scratch, that problem was potentially for lack of light, it's always possible to scrap it. Freezing dry and
But that's it, it depends. Now is if you want to target, now is a kind of target analysis, like one target, yeah, like one target from starch, it's like a dry or suffering fixes. In that case, yeah, of course, you can remove the first starch, yeah, because so you soak it in the water and you precipitate it, right? And also you can do some small color to remove the molecular based on the molecular weight in most cases. But it depends, really. Dry color or fraction detail. And sample presentation, sample representation, that reproducibility is a very important point. Now it's not the qualitative work. You have to get the quantitative, which means every time it shows the same yield, otherwise it will be a problem. Rather, instead of whether we can extract or that's not important because there is no method to extract any of all the compounds, but rather every time it has the same ratio, the same yield is very important. For it, it's a reproducibility because we are handling several hundreds of samples at the same time. Factors to be considered is a growing environment. Growing environment now is about the sample preparation. Growing environment, soil condition, climate. Yeah.
So, uh, uh, little bit before reproducibility. Uh, how many replicates uh, it's it's mandatory to do. Of course, depends the technique, depends the matrix, the sample depends. But for me, my opinion, if you have just one shot, one measurement in one day, in one equipment, one replicate, and one analysis, you cannot say that we have reproducibility. So if you don't have reproducibility, that means you cannot reproduce, of course, in another laboratory, for instance. and you cannot measure, you cannot quantify this. So, under the point of view of analytical chemistry, or on the point of view of the metrology aspect, these measurements, of course, you have information there, but under analytical chemistry, no matter.
Reproducibility, or let's say it's a replicates. How many replicates do you need for the sample? It's a very good question. Actually, I prepared one slide again. This was you are a little bit, you should have to be patient, but I can give an answer to you. Replicates. Why do you have to use a replicates? Because there's a variation, right? There are two kinds of variation: biological variation, technical variation. Now we are talking about the technical variation. Technical variation means analytical variation or sample preparation. I'm talking about the sample preparation. At least the sample preparation, extraction variation should be zero. So whatever is extraction is always is the same thing. Then analytical variation, like it depends. Estimates there are a lot of variation. Even depending on the instrument, there are instrument variation. But animal cases, because of low sensitivity, there is less variation. Yeah, technical variation is you have a sample, same sample, 1 gram of sample. How many samples you have to repeat the same sample? Like animal cases, one time is more than enough because there is less technical variation. But estimates case, even technical variation, you need the same triplicate. Now biological variation. Now if I say I have a ruler to weigh the Brazilian height, at least I have to check my ruler is correct one. That's the technical variation. After that, I have to collect how many Brazilian I have to measure. 10, 20, 30. It depends if you look the sample. If you have a gardening sample, like from your controlled greenhouse, maybe 3 more than is enough. But you are doing like a wider sample, like Alicia's cases. I collect the same sample, then you need a 10 sample because a lot of environmental and soil separation is. Usually biological variation, much bigger than technical variation cases. But biological variation, you have to consider depending on the quality of your sample. Maybe I can get back later. Yeah. Then factors because growing environment depending on the now is you want to do Brazilian orange metabolomics. But now depending on the region, they must have used different soil or different environment. So that's why now you collect in the two types of orange. If you found it different, maybe it can be from your origin difference, but it can be from different soil effect or origin effect. That is very careful. So that's why same growing condition and soil contamination. Soil condition is very important for private cases. So any kind of always factor. There are two kinds of factor: controlled factor, non-controlled factor, or you are expecting the factor, non-expected. Now my factor is orange metabolism, not soil effect, not climate effect. But you have to consider those who are already included in your sample. If you cannot control, what's the best way? You have to use one factor for non-interested. This is very important. Second one is contamination. Now orange metabolism. What's the problem? Where is the places? Depending on the orange places, some farmers they put the insecticide a lot. Some farmers they claim it our natural, we never use the pesticide. Now you compare this one. What's the problem? Change it. Then can you say, Florida orange? They use a lot of insecticide. Brazilian orange natural. You found influence. It's not because of orange different. It's because of treatment different. You have to be very careful. And also, most of insecticide, pesticide, is a hormonal type of compounds. So not only residual insecticide problem, also this insecticide, pesticide, they induce a lot of metabolites. It's very careful. And harvesting time. So depending on the harvest time, we call it circadian rhythm or biorhythm. Yeah. Depending on the time, metabolism is completely changed. Sometimes 10 times is different. Glucose in the morning here, glucose in the sunlight is 10 times is higher. Now your Brazilian orange you collected in the morning.
Florida orange you collected in the evening. Now you compare, it can be because of collection time difference, or even the microorganism cases you grow in the lab. But depending on the collection time, they have own cycle, the metabolites are changed. Now, your goal is genetic variation or genetic or related metabolism. You have to use the same collection time. And dry tissue, of course, leaf, stems, roots, but even in the same leaves, organs, they have a different kind of tissue. You have to be careful. And dry cases, fresh, freeze dry, depending on this treatment, metabolites are changing. And particle size, of course, particle size, you know the coffee, yeah, espresso should be fine powder, but drip coffee is a little bit less powder, yeah. It's depending on this one. Sometimes you grind very rough powder and fine powder, depending on the extraction, is completely different. One example here, Arabic citrus, one of the most famous model plants. Differently and depending on the accession, they are very different design spectrum. They are very different. Now, you want to treat plant hormone effect, yeah, on Arabic as a model plant. One of them use this accession. The other use this accession. Now they are different. They are different. And also they said genotype. The genotype, we call it genotype. But genotype is properly specified. We don't know how much they are expressed on us. Always, when you are doing metabolic variation, it's always based on expression type. And harvesting time, so now let's go harvesting time. It's a circadian rhythm, We believe, we had to believe, primary metabolites, sugar, starch, whatever, sucrose, they are changing a lot. So that's why only primary metabolites should be considered for circadian rhythm. But actually, it's not true. Here, this one is the primary metabolite here, by depending on the time, the lowest one, two times different. Fructose also 2 times different. Yeah? Sucrose here, 4 times different, and starch is completely 25 times different. So that's why if you choose wrong time, or if you choose a random time, that is a problem. And now this one is not only the small the primary metabolites like a quinine or progenic acid. They have a different 2 times different. So it means you decide to do non-production, to do another factor, not the production time. You have to be careful. You have to do one exactly same production. Of course, while the sample is very difficult, but for the controlled plants, like in greenhouse or in lab scale, even microorganisms, you have to be very careful. And tissue cases, leaf, stem, roots. Of course, everyone can distinguish what is leaf, what is root. You never mix up. But let's look at this. Now is tobacco leaf. In the same leaf, this one we call it vein, yeah? And this one is a fresh one. Now, when you measure spectrum, vein and leaf, it's a completely different one. Now, this is under the name of leaves. Yeah, can you see? Now, I want to test it. The acid side effect on leaf, Nicotiana leaves. Some plants, there are more veins. Some plants, there is only flesh material leaves. Now we compare with different one. But it can be because of the treatment. It can be also because of your long tissue separation. Nicotiana leaves, tobacco leaves is big. It's no problem to use for separation. But very tiny leaves, like Arabidopsis, how can I separate all the veins or leaves? That was the solution.
You increase sample. Just do not take just only take one.
So this is exactly this one. If you can separate, please do so. If you cannot separate, please homogenize very well. That was the point. Yeah. Now, small leaves. Of course, according to my suggestion, you have to separate vein or whatever. But if you cannot, you ground it very well. This randomize. This is very important. Right. And another point is drying. Freeze drying. Yeah. Here, why we want to use, particularly in animal spectrum, we want to dry water water is the key requirement for enzyme reaction. As I told you, when I harvested the sample, then enzyme started for the as a defense mechanism. This enzyme can degrade all the compounds like allene to allicin, allene to allicin, or glucosinolate. They are changed by myrosinase, or sometimes many chlorogenic acid can be changed. But you have to be very careful instability of compounds. There are two kinds of instability: biological instability, the second chemical instability. Some compounds after isolation is very stable, but if this compound is a biological material, via enzyme it can be degraded. What I'm talking about is enzyme degradation. So that's why water. I told you shock freezing is quenching. They say quenching because I want to stop enzyme. I want to stop enzyme and after stop enzyme, yeah, I want to dry because even dry the sample there is water, even the harvest sample there is water. This water can be the media, of the enzyme reaction, which I want to avoid. Two, so that's why now first one is enzyme is our enemy. To stop enzyme, first one is liquid nitrogen. But as I mentioned, if I am doing marine organism in the middle of ocean, Pacific Ocean, I cannot bring. What's the best way? Because you have to invent depending on the situation. So in that case, usually we put the marine organism. I'm not drying sample. I put the organic solvent like methanol or something like that. Then enzyme slow. Or if you have a sample, like a very low sample, I don't have any uh, liquid nitrogen or dry gas because in the middle of a mountain. How can you do? There is a simple method is sample, the old method is you can soak in the hot water, short time, very short time, hot water, then enzyme degrade. Another one is many cases you can invent. So if you have a target, it's very easy. Yeah? Now it's enzyme. I want to stop enzyme reaction. Second one is sometimes microwave. Microwave, few seconds, enzyme degrade. Enzyme stop. This is dependent on this. But usually liquid nitrogen is being used. And effect of signal also water is if you have a non-dry sample, big water signal is coming out and animal spectrum we want to suppress. That's why first physically I want to remove as much as possible water. There are several reasons why I have to remove the water because to avoid the enzyme reaction. Second one is the exact amount is not correct. And third one is the outcome of analytical big water signal comes out. So that's why so for some parts we want to remove water. And here now is water signal here. But if you remove the water, probably this some signal comes out. That's why we have to. There are two steps. First one, physically you remove by drying. Second one is water. Yesterday I mentioned noise cancelling. Water suppression you remove. So that's a two steps we remove water. But mass spectrum, you don't have to be worried because water cannot be detected in mass spectrum. Mass spectrum, no.
Sure. So the problem is when you're using very much NMR, so you have really to consider on that, and you did not use any kind of almost those solvent. But in my case, I use my spectrometry 73 ethanol water. It's like a protocol.
That's it. Okay. Because as I mentioned, HMS or GCMS, they are using fresh sample. It's no problem. Yeah, it's no problem. You can, if there is a protocol, already many people prove that the stability, the robustness, it's no problem.
But when you want to concatenate both analytical platforms and you have only the same sample, how should you proceed? Like right again for the MR, different sample for the same population, or dry, if you dry, if the water was there, this problem is going to happen. So if I want to use an MR and SMS for the same sample, and I
Oh, then now you have one sample. Now you want to do two method, yeah, HMS and of course the protocol of each method are different. Yeah, each method are different. NMR we prefer to use the dry sample. But HMS they always said it's a fresh sample is more than enough. Yeah. Then you have to decide, okay, if I have enough number of samples, I start from the fresh material, this one is a dry material. But I have very low amount of sample, yeah, then in that case, you have to start from dry material. It's depending on choice. So rather, you have to negotiate the situation. Yeah. And dry material, oven heating, I don't like it. Nobody likes it because it's a many chance, it's a quite higher chance for compounds to be degraded. So that's why we are using freeze drying or low temperature. But then if you say if you are drying the sample, if you are drying the sample, you are worrying. Many volatiles probably they will be lost, right? Yeah. Even freeze dry. But practically it's not true. This one is based on this paper. Now it's a fresh herbs. And then for example, all of these the volatile compounds, monoterpene, please look at this one. Fresh herb is a 5, and freeze dried 5.3. Even freeze dried is higher than fresh leaves. It's quite unexpected, right? So that's right. Freeze dried volatile is better. Even so, that's why in the food industry, when they are selling the material, they are using freeze dried because they keep flavors. And also, then this question is, how is it possible? Fresh leaves, we think is the maximum amount, but here, freeze dried is 500 even more. It's because, as I mentioned, when you do freeze dried, cell matrix is crushed, so yield is increased by the freeze dried. Of course, I wouldn't say the freeze dried is the best. You have to use it, but the message is this one: is freeze dried is not necessarily to degrade or to lose all the volatile. Even sometimes it's better. This is a But here, now it's 60, the oven heat. Now it's only half. Can you imagine? 30 degrees is lost. But freeze dry is different. So compared to other drying methods, it's quite different. And non-volatile cases, of course, freezing drying sample is much better than others. Why? Because it's a cell matrix, they remove the cell matrix effect to interfere in extraction heat. And factors to be considered, another one, particle size. Okay, now it's rough grind or high grind. So that's ideally, when you ground the sample, you have to use seed. The seed at 0.4 millimeter or whatever. But when you grind the fine powder, actually you don't have to do. But there is some impact. Particle size. Here. But this particle size, as long as you ground very finely, it's not a big issue. Yeah? And here, extraction method is, of course, extraction method is distillation, solvent extraction, cold compression, non-conventional like a supercritical. There are many extraction methods, but please keep in mind, I want to extract all. I want to extract all in high robustness. This is clear. So that's why, like, when you choose, supercritical fluid extraction with the carbon dioxide, supercritical state, it's nice. But the problem is, it can extract only volatile compounds. But my goal is for all metabolites. So that's why you have to choose it. Or if you choose extract like compression, for the compression, it's very nice. When you do for the compression, olive oil. Well, olive oil, the first one, because I want to use very fresh one. Yeah? Virgin olive oil is the first one. But I'm not selling my extract. I wanted to analyze why we have to use compression. Of course, there are all extraction methods. Keep in mind, I need the extraction in higher robustness. Second, it's very simple. Your ultrasonic cases is very simple. Ultrasonic cases is very simple. Now you can sometimes it's like conventional ultrasonication. Now flash and ultrasonic. Please look at this one. Please look at this one. Now it's always ultrasonic. Right? What's the mechanism of ultrasonication? It's like Euler spectrum. Euler spectrum when you are doing hypothesis. Anyone in the nature, anything in the nature, they are vibrating. They are vibrating. So they with their own frequency. Now compounds is here. Yeah? Matrix is here. We are vibrating. We are vibrating. So that's why if you give this frequency exactly same vibrated, I excited, I extract. So therefore, sometimes you may have some, you might be, you might misunderstand. If you have a fancy ultrasonication, you can control the power, 500 kilohertz, sometimes 50 kilohertz. Then everyone says, oh, I want to extend more, I want to increase the power, 500 kilohertz. It's not true because 500 kilohertz is not matched with my frequency. It never extracted, always the lower. Exact amount. Usually it's 50 kilohertz. Keep in mind, extraction yield is not for the power, the frequency, it's we need the exact frequency basis. But this kind of machine device, you cannot control, if it's a control power, it's no problem. Here, anyway, ultrasonication, you can exchange, you can transfer the compounds, metabolites, to the solvent to break the link between the matrix. But in the ultrasonication, one of the good thing is ultrasonication you can do in cold temperature because all the time before ultrasonication we are heating, the compounds is degrading. But ultrasonication in low temperature we can give energy, extract more. It's a cold temperature. You have to be very careful. I never found this problem, but in the textbook they said ultrasonication sometimes is the one. Well, if you are strong a long time, sonication, they are degraded to hydrolyzed. Do you have? Yeah.
As long like this because the extraction of vitamin C and the authors consider that when you use electrosonic radiation, you produce microbubbles within this region, not the best inside the cell. And you can
Yeah, of course. This is sure, of course. It's, if you have a minute, very micro, controlling is possible. But I want to remind you also, I, I don't have a target. I want to extract all in high velocities. This is
And there are another thing about ultrasound. If you have, let's say, 100 sample, and you in the first batch, you solidate it, let's say 10 minutes. The second batch, the temperature of water increase. So in the last batch, the temperature that you extract is different. So maybe you have, certainly you have difference. So you need to keep the temperature constant.
this is a very important one. If you give energy to the solvent to a bath, water in the bath, then energy, even you didn't give a heat, then it's getting warmer and warmer. So that's why, as he mentioned, now you 100 sample, you first batch you exchange. The second batch 100 is here, but it's already water is warmed up. Then the extraction is probably different. So that's why always I will put the extraction at the same time. And then now is another example. Depending on the some compound, there is a control flow here. You can find it is this book, this reference. Depending on the compounds, the optimum of the conditions are different. But now we want to use one method, cover whole method. Usually, if you do enough time, most of the compounds can be extracted. And sample preparation is our plant tissues. It's like we reported a long time ago in Nature protocol. Here, you plant collecting your greenhouse, and what are the best you ground? When you grind the sample, it's a heating coming out, the heat generated. So that's why always we put liquid nitrogen here. Liquid nitrogen, if you have a small number of samples, of course, if you put thousands of samples, it's impossible. But it's the same also, animal tissue, it's the same. Grind, and then you put here a sonicate, take out the supernator, and we directly go to the animal study. This is a problem. You understand? The important one is you have to grind. Yeah, grind. Do you want to use a miller You want to use water as well. In your cases, you have to be very careful. Coffee grinder. If you're using coffee grinder, it's nice. It's nice. Sometimes you can use for your kitchen, for your lab, but careful. There's a particle of iron comes out. Particle of iron comes out. Very small particle. That one poses a lot of problem in animal because the animal is a magnet. Your sample has a iron, then it's a problem. And also some people say, oh, I want to wash the iron, the animal tube with the tap water. Okay, then I try. But tap water contains, okay, it's not because of organic dirty material, dust material, but ions, yeah, many the metal samples are there. If metal samples included in animal, then it causes a lot of signal growth in cancer. Okay. Yeah, so grinder. So that's why in this case we want to use a mortar and that's a specialized for grinder sample. And then freeze dry. Yeah, freeze dry here. Yeah. And extraction, choice of solvent is very important. When you do extraction, of course, it's you don't have extraction solvent. There are hundreds of samples, hundreds of solvent, hundreds of compounds I have, but I don't have a time. That is the dilemma. Which solvent should I use? Yeah. If you choose water, you can extract only sugar. If you choose hexane, you can extract only fatty acid. But I want to see over. No. Then of course you can extract all the sample one by one, but it takes a long time. That is the dilemma. So in that case, now you have to fortunately extraction is completely different concept of solubility. Solubility means solvent and solute. It's very simple, whether I like him or not. If I don't like him, leave. Yeah? If I like him, it's leave. But now it's different. So extraction one is a matrix is involved. Every man they want to marry with the beautiful lady in Hollywood, right? But life is not that simple. Yeah. Always we have to negotiate with the situation. Now it's matrix is here. It's a compound, it's a matrix. I'm solvent. It's here. Now it's here. He should decide whether he wants to stay with the matrix or although I'm not very good, but it's better than him, he moved here. So that's why solvent is always extractability case. You have to think about the matrix cases. Usually in plant or matrix, it's very polar compound. It's like a polysaccharide cases. So that's why always if you give a big polar solvent like water, methanol, it can be dissociated to come here because water is coming here and then move here. Like taxol, paclitaxel is very soluble in chloroform. So that's why if you use chloroform for the extraction solvent from plant material, but it's less than 10%. It's very low. Why? Because of course solubility is very high, but taxol is very tightly bound to the matrix. Chloroform is not attractive anymore. He wants to stay with the matrix. So that's why you do methanol for solvent. Now is different story. He is moving to the methanol cases. This is also fatty acid cases. When you do extraction of fatty acid, lipid fatty acid cases, hexane is the best solvent to solubilize this. But when you do hexane solvent, it's not that the yield is not that high. Why? Because it is the matrix event. In that case, better to be polar solvent. Of course, now after dissociation material from the matrix, second step is solubilizing, of course. But this is a different story. The other is, in this case, we are using a little bit polar solvent. We tested in most of general compounds, many people say. So that's why any kind of metabolomic using methanol or ethanol and aqueous methanol. Why? Because even though solubilizing factor is sometimes lower in the molecular solvent, but extractability with the polar solvent is higher. That's the message. We cannot extract all, but it's an optimum solvent. How many metabolites? As I told you, plants is around 250,000 metabolites. Ideally, the physical or chemical character, each of them are different. It's not like the gene or not like the protein basis. Sarcomyces like the yeast, so 600 degree of diversity is different. It's molecular weight, polar, non-polar, non-polar. All compounds by target, which means on target analysis. If we have hundreds of solvent, which solvent should I use? Polar solvent. little bit for survey compared to this one. For my case, unknown plant comes up, which is what do I use? Usually we are using because depending on this one. But if you are using metabolic profiling, 50% methanol is my first choice. But if you want to do isolation of compound, usually you are using 80% of methanol, right? So anyway, aqueous methanol, 50% methanol is the best, it's the not best, it's optimal solvent to start the metabolic profiling. So optimum best, we cannot find it because there is no solvent. Optimum solvent should be developed on case by case basis. Yeah, but in general, no plant wants metal, for instance. So now many people testing, okay, whether it's true or not, same Arabioxis, acetone methanol is here, water is here, and water is here, and the methanol water is here, acetylene, acetone or acetylene is here. Now, problem is, my target is older compound. Now, if you choose different solvent, it's a completely different. This is the dilemma. Of course, one day, that's why I mentioned new trend analytical tool is imaging technique. One of the reasons is because they don't need extraction remote. Existent IPM technique, but still NMR, solid state NMR or imaging technique, there is still limitation, but in the future we will use this. But so far, so at this moment we have to use this extraction method. But situation is like this one. Which solvent is best? We don't know. Of course, we can do all together, but we don't have a time. Then in that case, please consider. For example, this one is water, it's only sugar. Mainly sugar is coming out. And here, methanol is more or less lipid comes out, for example. Now I want to use NMR. NMR cases, for example, now I'm not interested very much in fatty acids because we cannot distinguish whether to use this. So that's why, depending on now, I want to do volatile. Then you have to use this. But generally, for me, is methanol water is the first choice.
But
Yeah.
what is your opinion about use HRMIS, not for solid, but for heterogeneous material? Do you have
I
experience?
tried it, HR mass means mechanical spinning one. Or solid state instead of solid state and one solution in between. Some is turbid material, we can measure it. Some tissue culture, the tissues, they said it's quite good. But for me, when I do it, Arabidopsis, seed still. It's still is the resolution is not as much as I did. I couldn't find any reason why I have to use a basic angle spinning method because I couldn't get any additional information. That was the practical issues. Also it takes a time. Yeah. In the rotor sample, you have to edit everything. You have to edit the deuterium sample and data. If data is fancy, of course, I don't want to sleep. I can do experiment. Data is not that, but it takes a long time. And why should I? That is a dilemma. But in the future, magic angle spinning is another in between solid state solution. Maybe we can use it, but not very strong. Yeah, it's here, this species. And another one, it's not our group, oligochitosis group, they measured here. Now, it's depending on the solvent, CD, only need to go, whatever. The conclusion is, they found the difference depending on the solvent. But my goal is to cover whole metabolism. There is a big discrepancy. Which one we can use it, depending on the analytical method to follow. And second one is depending on your target. Of course, we are untargeted analysis, but which one is more important? This is
And what about the yield?
yield. And the robustness. Chloroform, I don't like it because even chloroform is very good. First one is chloroform can make some artifacts of alcohol. The second one is chloroform is sometimes yield is not reproducible. It's very very. And PCS chloroform reproducibility. Like a reproducibility is here. Now when you do T2, it looks okay. But when you do CD3CN, what's that? Acetylene, and T2 completely change it, right? So now it's reproducing. Here, this one. Message is, if you put one solvent, the reproducibility is high. Yeah? But if you mix up, of course, mix up. Today, I'm not going to have a very nice feeling. Yeah? Who cares? I mixed up. Yeah. That is a this completely. And also, volatile. So that's why one solvent is better, but it's not possible. So usually I'm using that kind of water. So that's why in my lab, I made a bulky solvent. Yeah, bulky solvent. Yeah. Then what go? 50-50. 50-50 is my first solvent. I'll show you the problem of 50-50 sample. Now, here Arabidopsis cell culture is a PCA. PCA means it's not the principal component analysis, it's a folkloric acid. Folkloric acid extraction. Folkloric acid they are using this one is for the animal tissue to stop the enzyme degradation, the metabolic degradation. Folkloric acid, ethanol, methanol, methylene chloride here. Now you see very different of this one, but different. Of course, we know different. Which one is useful? You have to choose. And another one example is there are many experiments. Is here all the methanol from 7-day old Arabic cells suspension culture depending on it's very complex, but message is they are different. And I think it's around 10 years ago, they published a lot of this kind of paper because there is a debating questions, which solvent should I use? But message, everyone is messaging, if you are using different solvents, this. And now is example of Arabidopsis is each all individual metabolites, glucose, glucose 6-phosphate, yeah, PCA 3, and ethanol 2, and methanol around 2. Methanol and chlorofluoro is 2.49. Now, it's a problem now. So that's why now we got a message. There is no solvent to get 100% yield of all metabolites. Yesterday I mentioned in a single organism like a plant, 30,000 metabolites are present. There is no solvent. Then which one is better? In general, the coverage is very important with the high robustness. In that case, 50% methanol, in my opinion, is the first choice.
Sure. And when with, I don't know more about alkaloids, but what do you think about using 0.1% acid in the water to extract?
I think I included these cases. I will show you.
It's always about
Here, now is, as I mentioned, I said, so 50% methanol is the first solvent. The first solvent. So one day I did some brush cut, the brush cut sample, and this one is controlled brush cut sample, and this one is infected brush cut sample. Now I did it 50% methanol. I concluded there is no difference. Right? But no difference. But when you change the slightly the methanol, 80% methanol is completely able to change. So that's why even you develop a new extraction method or protocol method, sometimes you cannot find it. That is a dilemma of general science. Always they want to find the difference. Yeah. So that's why sometimes, yeah, to find the difference is no problem. To find the difference, but to find the no difference is completely different story. Now you compare the two samples, Florida orange and Brasilia orange. You concluded they are not different. They are same. Then there are a lot of questions. How is it possible? Because you use only HBS, you use any animal. If you use other method, probably they are different. Right now, this GMO product. Yeah, GMO product. Okay, GMO product or wild product. And then you compare, you draw a conclusion. They are different. There is no change. But it's very dangerous because no change or no difference is very different. But if you find, okay, Florida orange is completely different with the one method, then its conclusion is different. So that's why when you find no difference, you have to be very careful. This one is really no difference, or if you use other method, it can be no difference. This is good. And here, big difference. So depending on the sample, always here. Now it's a long time ago to cover, to solve this problem. We use methanol. How much time do I have? Babino? Then I can continue this one. I talk too much today. Then is a two-phase extraction method, sample, and always we are use proper methanol water two-phase. Because one solvent is not enough. Two-phase solvent, proper part is no polar part. Methanol water part is a polar part. We separate it, we dry it, and we extract it. But the problem is it's nice, but it takes a long time because it is. And here now it's pro compression. It's a rosette. Catalantis rosette. Pro compression, I found the video. And polar compression, I found a lot of sugars. It's nice. One sample produces two extract. That's nice. But one sample takes 1 hour. So that is the problem. And here now no polar fraction from cannabis. Okay, I found it a lot of cannabinoids. And polar fraction, I found a lot of sugar. It's fine. But it takes a very long time. So this one is also water solvent. Here, provolone, fatty acid, for these cases. Now I have to remove. These cases. NMR, actually NMR, mass resonance cases. If the sample is rather not interested. So that's why I sacrifice polar fraction. Since then, I use the method because polar fraction. Here. Disadvantage of two difference. Yeah, very difficult to handle many samples. It takes a long time. Of course, it's not. No polar fraction, no information in the individual metabolism. Usually, it's only liquid pieces, which we have to use another expression. Not suitable for the medium polar metabolism because it's a proform and water fraction. There's middle polar, it's not so much, there is no fraction. So we will use it. So now we use, since then, for the NMR method, we developed this one. I need a dried powder. Okay? To save the problem, sample preparation, instead of adding normal solvent, I added electric deuterium solvent. 1 million. Of course, deuterium solvent is expensive, but if you use 30 milligram or 10 milligram of sample, you use 1 million of deuterium solvent, then extract it and take out the 300 microgram, then you don't have to evaporate, you don't have to do anything. It's a very simple method. So that's why at the same time, we can handle more than 1,000 sample, no problem. Even if we can extract in epidermal. So this one is a protocol, which one is very used. So methanol, yeah, CD314, and plus buffer, because this buffer is to adjust the pH. After that, this follow this one. Very simple. How long does it take? Only few minutes. Okay. But it can do parallel analysis. 100 sample with a rack. It's no problem. And here, now, we added here methanol is a catalanthal roseous sample because catalanthal roseous they contain a lot of indoor alkaloids, right? Indoor alkaloids. And alkaloids, we believe that they are extracted very well by the acid condition. Now I compare here methanol, TFA, and TFA, and our methanol, deuterium, pH6 method. This one is not correct. So that's why now, in terms of a general coverage of this one, although when you use selective X, why then we have to use acid condition? Because this one is targeted analysis. I'm not interested in other compounds. I only selectively extract this alkaline. So that's why we use the acid for alkaline extraction. But if you want to use other extraction method, this method would be perfect. So today I want to stop this, so I will continue tomorrow. Any questions?
If the people who has a question in the YouTube,
No questions, Professor.
no question. Okay, see, there isn't a question from the people in the YouTube. Okay, then we can close this part to
Every day delay, but one day I catch up.
You know, with training, is that So we developed.